My name's Cecilia Solhoff. I'm a wireless liaison specialist in the Wireless Bureau here at the FCC. Before we get started today, I want to go over a couple of housekeeping items. We do have sign-in sheets in the back. If you guys could all please sign in. There's one for attendees, one for the speakers, and one for press, if there's any press here. We also have some handouts back there. We have several PowerPoint presentations that are going to be given by the panelists today. We also have copies of the speaker biographies, and we have the agenda for the day. We've got the first panel's slides out there, and as the day progresses, we'll put copies of the slides out for everybody else. For those, we are streaming this live on the web. For those of you watching remotely, we do have copies of the presentations posted on the event website at www.fcc.gov/events/35-GHz-Workshop. We also have all the documents there. So we're going to start today with we're going to have some brief remarks by Julie Knapp. We're going to have a couple of panels and an overview, a little fireside chat, and a lot of different interactive pieces. There will be a chance for people to ask questions. If you're sitting here in the audience, we have some note cards and pens on the back table. We'll have a couple of staff, Milton and myself and a couple of other people around to collect the note cards from you here. Write your questions on the note cards. If you're watching remotely, you could do your questions by sending an email to livequestions@fcc.gov. Please include your name and the company you're affiliated with all the questions today. And now I want to introduce Julie Knapp. Julie is the Chief of the Office of Engineering and Technology here at the FCC.
Thanks, Celia. Good morning, everybody. It is terrific to see so many familiar faces around the room, especially to have a conversation about spectrum we can actually do something with. On behalf of the Wireless Telecommunications Bureau and the Office of Engineering and Technology, we're thrilled to have you here. We've got a terrific workshop set up for you today. I thought I'd take a couple of minutes just to talk about the background and characteristics of the spectrum we're going to be talking about. And if you'll permit me, I'll round the edges a little bit because if I really go into all the details, I'll be up here for 15 to 20 minutes. The spectrum that's the focus of today's workshop is the 100 megahertz of spectrum from 3550 to 3650 megahertz. This really emerged from the National Broadband Plan and the President's memo that called for identifying 500 megahertz of spectrum for wireless broadband, both licensed and unlicensed, to help meet the growing demands for spectrum and to spur innovation. The NTIA identified this 100 megahertz of spectrum for such use in its fast track report. But there were a few constraints for the spectrum. The band is used by high-powered Navy radars, and so the NTIA had established exclusion zones along much of the coast to both protect against interference to the radars and to deal with the situation of the radars interfering with the devices. But the analysis was based on basically traditional wireless cellular systems, ubiquitous deployment, towers, and so forth. So the FCC had invited comment on the potential use of the band, and some of the comments we came back was there was interest in the spectrum, but not for ubiquitous wireless deployment. In part because the propagation losses here are so high that you have to put in more towers, which means greater costs, so it was not particularly attractive for a wide area deployment. Meanwhile, there were developments that were going on other fronts. The President's Council of Advisors on Science and Technology was doing a hard look at spectrum, particularly on the federal side, and issued a report that focused on sharing, particularly noted the model that was used in the whitespaces in the TV spectrum based on use of a database and other techniques to gain access to spectrum in areas where it was available while protecting the services that were there. And on another front, we saw the evolution of small cells, in part similar to the Wi-Fi offloading model, where we had effectively a receiver that covered a very small area, but could pick up the load and then use other broadband methods for backhaul. So the notice of proposed rulemaking that the Commission issued towards the end of last year really represented a synthesis of all of these ideas. It proposed a tiered model of shared access to spectrum based on the PCAST report. It focused on small cells. And at the same time, it invited comment on how we could promote flexibility towards innovative and efficient use of the spectrum. Other ideas like how we might develop some synergy with the 50 megahertz of spectrum that's already available just above this band. So comments were filed in late February, and they presented a broad range of ideas and recommendations, and the reply comments are due in early April. And today's workshop is designed to bring together, as it said in the notice, the top innovators and thinkers in small cells, database management, and spectrum sharing to discuss technological developments. As Celia mentioned, we have got a real mix of presentations today. We have a couple of panels. We've got a discussion among the FCC, the NTIA, and the OSTP. There's also a brief tutorial on small cell technology and a technology exhibition that'll be available later in the day. And best of all, the chairman is going to stop by for some remarks a little later this morning. So with that, we'll kick this off. I did want to do two things. First of all, early in my career, when we talked about small cells, they were 1.25 miles. And the whole issue was, well, once you get down to those distances and you look for the spot, there's no building there, or they're in a spot like a school or a place you just couldn't deploy a tower. So the small cells we're talking about today are a lot smaller. You'll see later on, in the exhibition one, and they're this big. So when we talk about small cells, things have come a long way. And lastly, it would be remiss on my part not to recognize John Leibowitz and all. I don't think we would be here today without all of the terrific work that John has done, and I think everybody in the room knows that. And I just want to thank him for putting this all together. So with that, we'll turn it over to the first panel. If we can have the speakers come on up.
So as the speakers are coming up, the first panel today is Small Cell Technology, Network Design, and the 3.5 gigahertz band. The two moderators for this panel will be Paul Powell, who is an attorney advisor in the Mobility Division in the Wireless Telecommunications Bureau here at the FCC, and Bob Pavlak, who is the Senior Electronics Engineer in the Office of Engineering and Technology here at the FCC.
Good morning, everyone, and thanks for being here today. And welcome to the first panel of the 3.5 gigahertz workshop. As Cecilia said, I'm Paul Powell. I'm an attorney in the Mobility Division of the Wireless Bureau. With me is Bob Pavlik, Senior Engineer in the Office of Engineering and Technology. The subject of this first panel is small cell technology, network design, and the 3.5 gigahertz band. We have an exciting and diverse group of panelists this morning representing a wide variety of technological approaches towards small cell deployment and towards the 3.5 gigahertz band. And we think we've got a lively and informative discussion ahead of us. Now, without further ado, let me introduce the folks who are going to bring us the substance of the panel today. First, we have Professor Jeffrey Reed, Director of Wireless at Virginia Tech, Prakash Murut, Senior Research Specialist at Nokia Siemens Networks, Leo Cloutier, Senior Vice President of Corporate Strategy and Business Development at Bright House Networks, David Gurney, Distinguished Member of the Technical Staff at Motorola Solutions, Dan Lubar, External Affairs Director for the WhiteSpaces Alliance, and Chris Wyzorek, Senior Corporate Counsel at T-Mobile USA. Now let me turn it over to my colleague Bob Pavlik to ask the first set of introductory questions.
Okay. Thank you. The way we're going to run this is we'll have an introductory question for each of the panelists, and they'll have a few minutes to respond, some with presentations, some without. And so it'll be about 5 minutes each. We're giving Jeff a few extra minutes here in setting the stage with some background. After we go through the presentations, then there'll be an opportunity for questions and answers. So to start with, Jeff, What are the key technical issues for deploying small cells in 3.5 gigahertz, and what relevant projects have you been involved in, and what future technologies are needed in this area?
Oh, sure. Well, I think that the most interesting aspect going on now in small cell technology, the most interesting technologies under development are based upon self-organizing networks. The ability for these cells to do self-reconfiguration, self-optimization, and heal. And within that domain of self-organizing networks, looking at the initial configuration where we establish the radio parameters automatically, be able to determine what the neighboring cells are and be able to manage the connectivity. The idea is that with these small cells, they have to be extremely inexpensive, and we can't afford a technician to have to go out and maintain them or provide support for the consumer on it. So this is going to have to be very automated, as well as maintenance, because the environment will change with time. These small cells will have to adapt. They'll have to adapt in terms of the way that they handle the load and optimize their power for coverage with time to avoid interference. And kind of the third key issue is in self-healing. These small cells can go bad. And as we've seen, sometimes when cellular equipment goes bad, like repeaters go bad, it can cause a havoc to the network. If you collapse a broadband signal, for instance, into a narrowband signal, that signal can have a very devastating impact for a very long range. So we have to incorporate fault tolerance into these small cells and be able to recover. It'd be great if we can download new policies for these small cells. What we want to do is future-proof. And we want to give the FCC some flexibility to be able to change the spectrum regulations with time, and being able to do software downloads based upon new policies is a great way to do that. But if you make a mistake, it's always good to be able to recover from that mistake. So let's talk about where things are going in the research community. And I'll talk about this very much with respect to what's going on at Virginia Tech. My colleagues at Wireless Virginia Tech are working on approaches to self-configuration, self-optimization, and being able to heal. And kind of the key behind this is incorporating intelligence into the overall system. And it has to be very robust intelligence. You think about all of the knobs that we have and all of the meters that we have in adapting and controlling an LTE system. There are a lot, and with complex interactions. So being able to incorporate the artificial intelligence to help in the deployment and maintenance of these systems is going to be very key. We also need to be able to mix different types of systems together and understand what that proper mix is. And my colleagues at Virginia Tech, Dr. McKenzie, is looking at how you trade off these various systems and include dynamic spectrum access, and what are the strategies for maximizing overall capacity. The radar spectrum is the place that most people are looking to for getting additional spectrum. Radar does consume a lot of spectrum, and it is usually in a very localized area on a temporal basis. So it's natural for us to consider sharing with radar systems. That has some challenges to it in terms of being able to deal with some of these very high radar systems, being able to coexist, even if the radar is not co-channeled with the signal, it can still bleed over and cause significant adjacent channel interference. Being able to manage that interference through interference coordination techniques, and perhaps one of the early research issues that we're looking at is how might you cast radar coexistence within the ICIC framework for LTE. I think it is very possible to do that. Other areas, in terms of overall network sharing with small cells, does every service provider need to have his own small cell? Can we do some network sharing across that to be able to reduce cost? Particularly if the network provider doesn't own that spectrum, then I think it makes a lot more sense to share. Oftentimes, what prevents network sharing is trust between service providers. And the sharing mechanism, I think it does a lot to remove that mistrust, because if you don't like the deal that you're getting with your partner, you can always set up your own. But nevertheless, it's in everybody's advantage to share, and doing sharing on this massive scale, and to be able to do it with very low latency is definitely an important research issue. Energy reduction. One of the major costs for service providers, one of their major recurring costs is energy. How can we lower that energy bill? Small cells, I think, have the opportunity to do that. I think with a small cell, that being able to use renewable sources of energy starts to become more viable. One of the things that we've been looking at, the role of small cells in developing nations. Since these small cells consume so little power, you might be able to rely on solar power to help with these and power these cells, as well as to charge the user equipment. Experimental work. We need some experimental work. There are still those who are unsure about spectrum sharing. And the reason, or the way to overcome this is through some large-scale demonstrations of spectrum sharing. I think that's very, very necessary. And there is good cause for that, even though theoretically this should be fine. Sometimes you get systems that are very large, and you get what's called emergent behavior. At a different scale, the overall system can behave differently. And doing some experiments can certainly help the community, help regulators, manufacturers, and service providers gain the confidence that they need to invest in this technology. Security and information assurance. One of the things that we're looking at Virginia Tech is security vulnerabilities of self-organizing networks. These networks do open up new potential security holes. For instance, what happens if one of the femtocells or small cells starts to lie about the conditions in the environment? How would you know that? And that possibly could deny access to others by introducing lies into the overall environmental awareness that this network or the node is supposed to produce. And finally, one of the things that we are working with the FCC on is research that would help support the regulatory and enforcement environment, helping to automate the enforcement process. As we scale up in these nodes, we're not going to scale up in the number of regulators, so we need to automate that.
Good. Well, thank you very much, Jeff. Appreciate it. Just as a brief reminder, when the panelists speak, if you can speak into the mic, we're streaming this session over the web, so that's important. Just want to make that reminder. Next, Prakash. Nokia Siemens Networks has been very active in the development of innovative small cell solutions for mobile carriers. What opportunities do small cell deployments enable these carriers, especially in 3.5 gigahertz? And can these operations effectively coexist with incumbent users?
Thank you, Bob. To answer your questions, I have a couple of slides here that I would like to go through. We do see small cells in 3.5 gigahertz as being an integral part of the network and could play, a key role in expanding coverage, capacity, and then provide new opportunities, some of which, the FCC has mentioned in the NPRM. Why? First of all, there are two TDD bands, two TD-LT bands that have already been defined in 3GPP that cover 3550 to 3650 megahertz. So the specs are already there, and we can leverage those specs to develop the equipment and the devices that could be used worldwide. So this band is a global band, and really FCC can lead the way here by making sure that we can use those 3GPP specs that are already there to develop the ecosystem. So 50 megahertz would be in band 42. That goes from 3400 to 3600, and then there's another 50 megahertz of the FCC spectrum that would fall into band 43. We definitely recommend the FCC to align, the spectrum with those specs. How 3.5 gigahertz small cells could be used? We see that as enabling capacity boosting to an LTE FDD overlay, for instance. So the TD-LTE system 3.5 gigahertz could be used as an underlay to provide capacity boost to 700 megahertz, for instance, or the spectrum bands where operators have deployed LTE or are deploying LTE. And I would also like to mention that, as you all know, public safety is also using LTE to deploy, broadband system at 700 megahertz. At NSN, what we've done, we've trying to get, dirty and with actual small cells deployment. So we've deployed small cells in a true hot zone in Chicago area and trying to understand the issues around wireless backhaul, for instance. Trying to understand the RF performance validation. And also how to deploy on street poles, what it takes, and also how to work with municipalities to do those. And we are deriving key learnings, and that hot zone was deployed along a train station, so we have thousands of people commuting through the train, and we have shops, movie theaters around. So it was a real true hot zone. And we've derived key learnings, and one of those is that, if we have dedicated spectrum for small cells, we've seen an enhancement in the capacity improvement that we get. So, compared to the macro. So if a macro is on a band and then the small cells are a different band, there's definitely some increase in the capacity. And simply because you don't have interference from the macro base station on the same frequency. There are some techniques that can be used to mitigate those interference from a macro system to the small cells if are operating on the same frequency. And I think Professor Reed touched on some of those techniques around EIC, etc. But definitely, operators may opt to use 3.5 gigahertz as a dedicated spectrum for small cells. And then, in terms of Bob asked a question about interference mitigation. There's one new scheme that we've been proposing, and actually is getting a lot of traction in Europe, called authorized shared access. It's very similar to a framework that FCC has laid in its NPRM. One major difference, though, in our proposal is that we would include non-critical users, like operators, which also need quality of service in this second tier of users. And we'll let features like Sun manage the traffic between those two categories of users. For instance, Professor Reed also talked about Sun in his presentation. So we don't see the need of having a free tier approach. A two-tier approach, the only guys who need priority of incumbent users, and the rest of the users could be managed through Sun. And LTE has Sun, as one of the features, as you may know. And then I would conclude by saying that, we are taking 3.5 GHz and also ASA, authorized shared access, quite seriously in NSN. And we actually had a joint demo with Qualcomm at the Mobile World Congress a couple of weeks ago, and we hope that we can do this demo again here at the FCC, maybe on a future occasion. So thank you. Thanks, Bob.
Okay, thank you, Prakash. Next, Leo Cloutier from Bright House Networks. So Leo, Bright House is a U.S. cable operator that is a key member of Cable Wi-Fi, a consortium of cable companies that have established a network of tens of thousands of Wi-Fi hotspots for customers. What does the future hold for small cell and Wi-Fi network deployments, and in particular, how do you see such deployments incorporated in 3.5 gigahertz?
Thank you. Good morning. So yes, Bright House Networks, we're a cable operator in the U.S. We're the 6th largest cable operator. We have about 2.5 million subscribers. We're what you'd call a regional operator, mostly in the southeast. We have begun deploying Wi-Fi, so we've done a heavy deployment of Wi-Fi. We're located in Central Florida for the most part, and for example, we probably have over 5,000 access points in both Tampa and Orlando metropolitan areas. So when you look at that sort of a deployment, maybe half of them are outdoors, half of them are indoors, and that sort of a deployment is a small cell deployment. As a cable operator, we have coaxial cable out in the outside plant, and that cable plant can be used for both backhaul as well as power. So it solves some of the problems with how you get a small cell network built. And I think some of our experiences with Wi-Fi are very relevant to the small cell space. Dr. Reed, when I listen to some of your characterization of the problems, I think, well, these are the problems we've been dealing with over the last couple of years. When you put in 200 access points into an arena for basketball or hockey, you have to deal with many of these problems, sort of this controller architecture that controls power levels and interference between cells. So we've been dealing with a lot of these problems on the Wi-Fi side. And again, as a regional operator, we're working with other MSOs or other cable operators in the U.S. to provide a somewhat of a national footprint. So if you go to New York, our customers could access Wi-Fi through this cable Wi-Fi SSID, or LA, or many of the other cities in the area. And I think Northern Virginia, there's some here. So that sort of thing we've been getting experience with. When we look at Wi-Fi, it's unlicensed. I think we are doing something innovative. We're taking a home-based service and we're investing to create a mobile broadband service that's different than what you get from an LTE provider today. It's a capacity-based service in specific areas where there's heavy demand, and so I think that does bring innovation to the American consumer. I think that innovation is good because many of the devices they carry don't have LTE in them. They all have Wi-Fi for the most part. Any mobile device that you have has Wi-Fi, and that's not always true for a 3G or a 4G interface in them. So I think when you look at that, we're doing something innovative. We're trying a new business model, and I think it's a valuable service for our customers. I think they recognize the value it brings to their home high-speed data service. However, when you look at 2.4 gigahertz and even 5 gigahertz, the question of exhaust of that spectrum being fully utilized, it's in effect no different than licensed spectrum. In licensed spectrum, we deal with exhaust and needing more spectrum to support demand. Similar types of concept with unlicensed spectrum. So when we look at 3.5 gigahertz, we think a small cell type of an approach with 3.5 gigahertz would be something that we could incorporate into our networks, and we would find value in it. I think again, we have experience doing it, and I think many of the problems that you talked about are the things that we've dealt with when you put so many up in an area. I think when we look at 3.5 gigahertz, making it a small cell band is something that helps with the interference issues, and it could help us in our business. And I think specifically, everybody at this table would say if you want to solve the capacity demands over the coming years, you need to go to small cells. So I don't think there'd be a lot of debate about that. I think we as a group should make sure we're thinking about a global ecosystem as well. Wi-Fi is a global ecosystem. It's in everything. If we do something in the U.S. with 3.5 gigahertz that's not adopted elsewhere, or that isn't easily part of a harmonized global approach, the ecosystem will flounder, and that won't be good for anybody. And I think I think some of that is why you see Wi-Fi everywhere, and you don't necessarily see the same ubiquity of LTE, at least not yet. So that'd be one thing I'd like to point out. Maybe those are some of the key points I'd make, and can follow up with questions.
Good. Thank you, Leo.
Dave, Motorola Solutions is a major provider of communication services to public safety, healthcare, and government users. How do you see small cell deployments, and specifically the 3.5 gigahertz band, contributing to the development of quality-assured network solutions for these critical users?
Sure. I think you'll see small cells impact quite a few areas for those customers, including things like public safety incident scenes where you need additional capacity, things like critical infrastructure applications. Those would be both small cell and wide area networks, as well as the hospital environment where you might see more QoS assured small area networks than what's available today in the unlicensed bands. So we'll jump to my slides here. And taking a step back, I think we see this as a large opportunity and really a new opportunity for truly dynamic spectrum sharing. We're talking about a large amount of spectrum here. You should be able to support a wide variety of services, get them to coexist, wide variety of services and service types. And you also have the opportunity to sort of segment the spectrum into different operating classes. And that I'll talk a little bit more about that later, but that does allow some new things to be done. Of course, it's a new way of doing business in terms of spectrum management, where these high-level rules drive operating classes and spectrum usage. We think it allows a lot of advantages, such as adding new services into the band and also dynamically allocating spectrum among those uses to where it's most needed. So it does give the regulators some new tools to do that on a rapid basis. If you look at the TV bands today, near real-time database technology exists, and it's certainly capable of meeting the needs here for enforcing this orderly coexistence. Database update rates on the order of minutes are possible today in the TV bands. You have roughly 15-minute update cycles for dispersing the registration information for things like wireless mics. Certainly the technology is there today to do near real-time database updates. Of course, the advantage of that is that it allows improved spectrum efficiency and utilization. There's no more static allocations to different services. When a service goes offline, other services can jump in. So it's a very exciting possibility. Of course, as Jeff mentioned, database security and privacy are key issues here, protecting incumbent and priority access user information. We've actually got a research program going on with Virginia Tech in that area. So there's definitely some new problems there to be solved. And in terms of what we feel that the priority access tier is really the key to all this. It's what differentiates it from TV WhiteSpace, where everybody's lumped into an unlicensed category. We feel that having these well-defined levels really makes the spectrum more usable. There's a lot of services. If you look at a lot of the comments that came in, a lot of the users were really asking for some type of guarantees of access or QoS, and we feel that having priority an access tier with well-defined priority levels helps you do that. In terms of potential applications, some of which I mentioned already, there's a wide range. Certainly, we also do business in the enterprise commercial class of wireless LANs for businesses. That includes can include things that the carriers are interested in, such as commercial hotspots and femtocells for offloading. Some QoS guarantees there would be very helpful and certainly increase the value of the spectrum. The hospital, small area network cases, things like patient monitoring, another area where obviously high priority and high QoS usage is important. Those are typically indoors and low power type applications and otherwise have similarities to the enterprise class. And then an area that we're very interested in is high reliability incident scene networks, so sort of on-demand deployments, typically very time limited and very geography limited deployments of additional capacity. And of course that requires the things that we've talked about in terms of near real-time databases and priority access. There's also the possibility for higher powered wider area networks for critical infrastructure uses, smart grid type applications, and also of course the WISP usage that's already there in the 3650 to 3700 band. And then anything else beyond that we feel kind of falls into the general access tier of something that looks a little bit more like unlicensed type usage. Some other considerations that I mentioned up front is it may be advantageous to segment the spectrum into different use classes. Maybe that's done on power, based on power levels. Maybe it's done on priority levels. The order did talk about these high power operation zones. So that may ease some of the interference management issues. It also, as I mentioned, does allow you to sort of dynamically allocate spectrum to different uses. In terms of the incumbents and services that are modeled in the band, that can be done at a very high degree of accuracy in geolocation databases. Realistic modeling of the incumbent protection zones needs to be computed based on the actual deployment parameters of the systems that are deployed to protect the incumbents from interference. It's not a one-size-fits-all model. We also feel that you can take into account the detailed operating parameters of those systems, things like transmission power levels, out-of-band emission levels, interference tolerances, antenna heights, and the like. The other thing that's important for the operators, the secondary users in the band, is what kind of interference environment do they have to operate in. And we feel that the incumbents can make those decisions. The priority access users can best make those decisions on a case-by-case basis. Perhaps consumer equipment you wouldn't want to do that with, but we feel we have the knowledge or can have the knowledge to make those decisions. And then finally, spectrum sharing test beds are very important in this area. As Jeff mentioned, we want to prove out the concepts. We're looking at several opportunities there, and we encourage the Commission to move expeditiously in this matter. Thank you.
Thanks, Dave. Dan, the members of the WhiteSpaces Alliance have extensive experience operating in shared spectrum bands, often on an unlicensed or lightly licensed basis. What opportunities do you see for unlicensed or lightly licensed applications in the 3.5 gigahertz band?
Thank you for that question, Paul. Quick answer before I go through my slides. Obviously, that spectrum, the 3550 spectrum, has the same opportunity that any spectrum has. I would sort of push us in the direction of the PCAST report and its discussion of the currency of spectrum and how important it is for nation states to put that spectrum to use, make it part of the economic value that country has. That's a really key point, no matter what the spectrum is. I guess the first thing to say here is that I really just want to thank a few people. As Julie mentioned, OET and the Wireless Telecommunications Bureau, thank you for putting this event on. I think it's very important to air out some of these things. And, of course, thank you to OSTP and PCAST for the PCAST report. As far as our membership is concerned, it's really a seminal document. If you haven't read it, you should. Briefly about the WhiteSpace Alliance. The WhiteSpace Alliance is a member-based global organization that promotes in a technology-neutral way the development, deployment, and products and services associated with WhiteSpace spectrum. Now, just to be clear, even though everybody these days is talking about TB whitespace, many different bands of spectrum have white spaces in them, and we can get into the rest of what that means later. I think at this point, I also want to acknowledge one other thing. For those that know, on Monday this week, the TAC committee was meeting. 2 years ago, I just wanted to give those guys also a thank you, because basically in the chairman's report, they talked about what we're doing here today, and that was a pretty instrumental thing. I guess at this point, I'm going to jump into the infrastructure issues that we're here to try to address with this panel. Now, this is an eye chart, and I'll just say that the reason I put this up is from a study that Industry Canada did a few years ago, and it outlines by technology and population density and cost and complexity where different technologies lie. And off on the bottom right corner there, if you're careful, you can see that wireless is sort of high up in the cost complexity space. There's a reason for that we don't have time to go into today, but what the WhiteSpace Alliance is interested in doing is bringing down the cost complexity of wireless, and that's what small cells really mean. The idea of being able to do that means that you can reduce RF interference by using a mechanism to minimize that interference. And in these bands, we're looking at databases. To jump a little downstream here, automatically minimizing interference is a dream, but that dream is probably going to be quite possible based on the ability to do some things with PAWS. PAWS is a database standard that is from IETF, and it's going to allow for our favorite thing in the Alliance, which is dynamic spectrum access. That access gives you the ability to dynamically use an access spectrum, minimizing interference and maximizing what I mentioned before, the economic value. It also levels the playing field for all players to come to the table to use that spectrum. So that's a key piece that really is pretty contentious from time to time, and it's important for spectrum policy folks to understand what PAWS is really going to allow there. The next thing to talk about is spectrum policy. PAWS is sort of just the beginning there. It's worth mentioning that radio systems processing power and the evolution that spectrum management and spectrum policy is going through. I went from the eye chart to the fun one. So anyway, the idea here is that with better processing power in radios and spectrum access innovations like PAWS and other standards, and what we're going to all try to be doing here in 3550 and the Commission's filing, it's going to be pretty exciting to see what comes of it. Interference mitigation is really at the basis of all this. And databases may enable other forms of benefits too. I'll just throw out one example. It has to do with enforcement. If you imagine for a moment that the PAWS infrastructure of internet-connected radios gives you the ability to find out where interference is occurring. Right now, there's a lot of people from the Commission's Enforcement Bureau that go out in the field and mitigate enforcement issues. What if the database was a tool to be able to do things like lowering cost of interference mitigation? It very well could be. I'll finish up with one other thing, and that has to do with Cisco's VNI index. just so everybody's clear about the bigger picture of small cells, and then I'll hand over to my colleague. The VNI, the recent one that was, I think, published a couple months ago, talks about 33% data offload on average from cellular network infrastructure to Wi-Fi. And let's face it, that's a really great thing, because it brings 3GPP standards and 802 standards into an alliance that creates a better outcome for both of those infrastructure, stakeholders. I'll just say that that's forecast to jump up to 46% in the Cisco document, the recent Cisco document. So we all have a requirement and a responsibility to be able to make this work. And with that, I will yield back.
Thanks, Dan. I just want to take a minute to remind everyone in the audience that you can submit questions at any time. Please don't wait until the end. And folks who are watching via webcast, you can submit questions to livequestions@fcc.gov. Chris, how important are small cells and heterogeneous networks to T-Mobile's future network deployment strategies? And how do you envision the 3.5 gigahertz band factoring into those plans?
Thank you for inviting us. We're very pleased to be here today. I think to answer your question, they're very important. In fact, there's a key part of the transaction that the FCC Wireless Bureau, thankfully, we very much appreciate you approving it yesterday. We're going to be acquiring up to roughly 10,000 distributed antenna system sites for Metro PCS that will be deployed, and those are critical for deploying in particularly capacity-rich environments, capacity-demand environments. Heterogeneous networks is kind of where we see as kind of the overall topic we use for small cell deployment. And this is the idea that you have the macro cell, and you have everything below it. You can get a wide variety of different opinions of what is a micro cell, or a pico cell, or a nano cell, or what have you. But we use the overall catchphrase of heterogeneous networks. And it's based upon three basic premise. First, you have a topology issue, the type of environment, the geography, the number of people, the density of the environment, and the people who want to use spectrum that's going to drive this matter. The technology that's available, as we've been seeing, Prakash has shown earlier, small devices getting smaller and smaller, especially on the base station side and infrastructure side. It makes it possible to provide these in smaller environments. And finally, spectrum, which is the raw material. If the 3.5 gigahertz band was only 50 megahertz involved, I don't think we'd necessarily be having this workshop. But when we look at 100 megahertz or potentially even 150 megahertz, it gets to be a lot more interesting and a lot more opportunities for folks to be able to make use of this spectrum. And so we think that by focusing on these technologies and these three concepts is where you'll see the 3.5 gigahertz band take advantage of it, or be taken advantage of. T-Mobile, I think we're unique in the sense that we've been developing and using heterogeneous networks for both in the macro cellular, the GSM, the UMTS network, and then also Wi-Fi. We are the first carrier, in fact the only carrier as far as I'm aware of that in the U.S. that does what's called unlicensed mobile access, UMA, and then with a subsequent follow-up called GAN, which allows you to make Wi-Fi calling. So you can bring your T-Mobile phone, bring it overseas, hop on a Wi-Fi hotspot, and you use your regular plan minutes and the like. We think that's very, very efficacious. So we've been using these different technologies. We think another point is that was brought up, I think Prakash as well brought it up, is the fact that when you get into these kind of situations where you have more dense use cases, that you probably will have a situation where the infrastructure will be shared among multiple carriers. That will hopefully solve a lot of issues. I mean, first off, if you're going to have multiple carriers using a spectrum and it's going to be a potentially TDD-developed use, it's going to be just very difficult to do coordination. And so if you have a single equipment vendor and a single deployment and the like, and all the carriers share that, it makes it potentially a lot easier to use as a practical matter. But then there's something to keep in mind, I think, for the carrier perspective, if we're going to make use of this 3.5 gigahertz band, is how is the spectrum actually going to be used? And if it's, as I said earlier, 100 to 150 megahertz gets to be very exciting. When you start decreasing the amount of spectrum that's available for consumers to use, if it's only like 50 megahertz, well, then it gets to be much less exciting. 50 megahertz at 3.5 gigahertz is not nearly as exciting as just using a macro cellular environment and more traditional bands, AWS PCS bands, or the BRS bands, where you can get much larger swaths of spectrum, which have better propagation characteristics as opposed to just having that narrow there. So we think that's something that the Commission and the end users and deployers and all the people involved in this discourse community should be considerate of, the fact that the thing that makes this band so great is that it's a large swath of spectrum that hopefully a lot of people can get access to. And as we reduce, if there is anything that ends up reducing that amount of spectrum, it gets to be much less attractive for end users and everyone involved. So I think that's very important to keep in mind. I think I've passed the slides, but with that, I think you might back time back to the questions.
Okay. Well, thank you, everyone. Now we're going to move on to the question and answer portion of the panel. So I'll just throw out a broad question here to start. We've heard a lot of different perspectives on the band and the technology that's going to go into network deployments here. What technology do each of you think is going to be the biggest driver of small cell shipments over, say, the next 5 years? And anyone can jump in, and then the rest of you can.
Wi-Fi? Actually, I'll just jump in and really briefly say it's going to be the demand side. I mean, let's face it, the consumer marketplace is really going to drive it. That just seems like an intuitive answer. As far as the WhiteSpace Alliance is concerned, I don't have a sense of what's going to happen necessarily. I mean, well, the U.S., I won't talk about that. I'll talk about overseas. A lot of countries are motivated to use the spectrum, especially television band spectrum, in the way that we might be using 3550. And that's an interesting point to throw out.
I was serious about my Wi-Fi comment. U.S. cable operators in cable Wi-Fi, it would be interesting to count up over the next year how many Wi-Fi public access points we deploy in 1 year, 12 months, and then compare it to how many LTE small cells are deployed over the next 5 years. Wi-Fi is a small cell technology, and it's going to have more volume over the next 5 years. I believe that.
Yeah, Paul, this is what operators are telling us. So I think it's going to be a mix of Wi-Fi, obviously, but also LTE. I mean, they want, in the same box, they want, several bands of LTE, not just one. They want backhaul, they want Wi-Fi. So, us as an industry, we need to figure out how we put all of this in a box that can sit, on a street pole, for instance. So that's going to be a challenge. So it's not just Wi-Fi. We are also hearing about LTE, so not just Wi-Fi. If we look specifically at 3.5, though, how long would it take to develop Wi-Fi for that band? It's going to take a year, because right now Wi-Fi is in 5.x or 2.4 gigahertz. We already have LTE standards for 3.5 that could be used. So I think by deploying LTE for that specific band, 3.5, I think the standards are already there. So the way at least 3GPP works, usually they wait for the regulator to define the rules. Then they go out and specify the band. So if FCC is going to take maybe a year to finish the rules, and then you need to wait another year to define the standards, and then another 1 or 2 years to get the equipment in the market. That's 3-4 years from now. We already have the LTE standards, so why not use that specifically for 3.5s?
Yeah, if I could second that, I think using LTE in particular and trying to work within the standardized process will expedite the process. Because when there's no standards involved and no standardized technology, you're going to slow things down. And in reality, if we're trying to see small cells even manufactured within 5 years, the only way to do that is using an existing LTE standards, because you're not going to go from allocation NPRM to having anything manufactured within 5 years without using an existing LTE standard.
Oddly, what could drive it is reliability of the spectrum. And I know there's a lot of criticism for spectrum sharing in that regards, but the ISM bands are very cluttered right now, and 3.5 represents the new frontier. So it may be supporting quality of service that is really the attractive aspect of 3.5 small cells.
And the other thing I want to add, and I think Leo mentioned, taking a global approach to this ban. I mean, in many countries like Europe, this ban has already been auctioned. It's being used by WiMAX right now. We all know that WiMAX hasn't really picked up. So many of these operators are looking at the opportunities, and migrating from WiMAX TDD to a TD-LTE solution is, easier than going from WiMAX to an FDD-LTE because you need guard bands, etc. You can time synchronize your WiMAX and TD-LTE network and make both coexist. So that's one point. The other point is, Japan, for instance, is starting a similar process like the FCC. And with the big operators, the KDDI, SoftBank, the Docomo, all looking at that spectrum as a licensed band, not unlicensed. So, whether it's Europe or in Japan, all of these guys are looking at this spectrum as a licensed band, not an unlicensed band. So license should definitely be part of the equation here. If we just do unlicensed, would probably be the only one doing that, and then getting the devices to support, just the US ecosystem might be tricky.
So we have views about Wi-Fi and LTE technology, also a large amount of spectrum. Given the diversity of the technologies, but also given the relatively short range of this band with low power and high frequency reuse, what are the views about how different kinds of networks might be able to coexist in this band across carrier, enterprise, and consumer networks?
It's important to ask that question architecturally, topologically, when you're designing and building a network. With respect to my colleague from T-Mobile, his talked about heterogeneous networks. The reason that small cells are important in high-density urban environments is that you can create a low-power solution that has high throughput and also, the ability for a lot of reuse. The higher frequencies allow for more reuse in smaller cells. That's architecturally why this band is important for offload, for unlicensed use, and I think the Tier 3, the GAA, is absolutely a wonderful place for innovation. And as I mentioned in my comments, the WhiteSpace Alliance is really trying to be technology neutral. We focus on leveraging the asset and not building a monoculture. And I think it's really important, on the one hand, to be able to sell chips, to be able to manufacture products so you can scale and do things on a global basis. But I also think it's important to be able to allow for innovation so that you get the economic value and innovation around a new band of spectrum being introduced. That's all I had to say.
Other views? Can Wi-Fi and LTE coexist in this band?
They already do. I mean,
in the band.
Yeah, that is to say, if you will, different standards and coexistence assurance between standards or different air interface mechanisms. Let's face it, each of those standards has a different, I guess I would call it interference problem. Having guard bands, duplex gaps, there are mechanisms to create coexistence between different standards operating in a band, especially if it's 150 megahertz wide. So that would be a good, quick answer.
Other views?
I think they can coexist. I think we heard Dave talk about prioritization and who gets priority, and I think giving network operators a higher priority. We actually do very actively manage our networks. I think that could be a component of it, and I do think I agree with making sure we're not on an island in the U.S. with some funny standard that nobody else uses in the end, just because we had to please a lot of stakeholders. So those are some of the things to.
A lot of the coexistence can be handled in the database as well. Systems with poor out-of-band emissions, for example, like Wi-Fi, they'll have larger standoff distances from other services. So, I mean, it's all very technically possible to help them coexist in the database.
Prakash?
Yeah. So, the framework that the FCC has laid out, where you cannot use the GAA when proprietary access users are using or where they are using. I think that some sort of time separation or geographical separation would work. But if you want them to be using the spectrum at the same location, same time, Wi-Fi use a CSMA, protocol. So we'll listen before transmit, and if a channel is not being used, they won't transmit on the channel. They'll defer and maybe try again later. With LTE, what we'll do, we'll adapt its modulation and encoding scheme so that it can still transmit even if a channel has some interference on it. So what could happen if you allow Wi-Fi and LTE to transmit at the same location at the same time is that LTE would be using the channel most or all of the time, and Wi-Fi would be, just the background trying to get access to the channel. So I think some sort of time or geographical separation would be needed. Otherwise, we need to tweak the LTE standards or the Wi-Fi standards so that they can coexist at the same time at the same location. So those are different things.
Yeah. Forgive me for saying something that maybe sound heretical here, but Wi-Fi is actually a pretty dirty standard when it comes to using the spectrum. I mean, it's designed to be used to be able to do lots of sharing and be able to work with a non-synchronized networks. And LTE is very optimized to work with a synchronized network. And so there's a trade-off. By virtue of having a very high throughput situation with LTE, you have much limited tolerance for having this situation. And it's just the fact of reality. If you want to go to a network that's very high throughput, which we think this is a good band for, then we think you ought to be looking at LTE. You look at a global standard. You try to work with the existing standards, as Prakash mentioned, and you try to figure out the policy mechanisms and levers to make that work. If we're looking to kind of look on the Wi-Fi approach, which is the straight unlicensed, and everyone can back off as they need to, well, you're not going to necessarily run into a very efficient spectrum utilization, I think. I mean, it's the reality of it, unless there's advances coming into the Wi-Fi world, but just as a practical matter, it's not that way, and especially not within the next 5 years.
Okay. Jeff, do you want to jump in?
Yes. Actually, I don't think this is going to be a problem for some time to come. It's 100 to 150 megahertz of bandwidth, and as long as we have appropriate frequency agility and we have database coordination, it's going to be a while before I think we start to see this problem. And I think it's a very doable problem. I can think of several different ways to approach this problem, and we have time to think it through. I don't think we should panic about it. It's just not going to be an issue for some time to come.
Okay.
Thanks.
Robert, if I might just add one other comment. What we're really talking about here in a Wi-Fi context is exponential backoff was a best effort mechanism to gain and access and use spectrum. If you add databases to that mix, I'll echo my colleagues here, all of a sudden that exponential backoff mechanism that gives you essentially access to the medium can change and be more coordinated and maybe not necessarily as relied upon. I'm not saying that TDD is a terrible thing. I'm just saying that there is a need for best effort services in this band, and that's where you'll see innovation similar to what happened in the 802.11 world in the beginning. Just wanted to add that.
Okay, Prakash, you mentioned some of the rollout timeline issues here, and I guess I'm wondering how much of a challenge do you see to rolling out services in the 3.5 gigahertz band, given the presence of the incumbent operations in the band, and what information do folks need to roll out the services here about those incumbent operations?
Okay, so if we know the somehow the characteristics of the incumbent, definitely the LTE network should be would be able to adapt. But I understand that some of the information might be classified. But in the LTE case, for instance, we can leverage the sun feature. So, for example, if the sun can have the radar operation characteristic from the database, what FCC has called the SAS, Spectrum Access System, for instance, and then it can adapt itself so that the transmit power stores below a certain threshold, so that it doesn't interfere with the radar system. So that's something that could be done, and also managing interference among the different small cells, through the sun again is something that could be done. So I guess there need to be some information available to us, from the incumbent, so that we can adapt the LTE network to prevent interference to the to the radar system. And also the other way around also. I mean, if somehow we have a connection between the Sun server and the database, and the radar system comes on and say, I need that spectrum for, I don't know, the next 1 hour or 2 hours. The Sun can then, either lower the transmit power of the devices and maybe the access points, or it can even just turn off everything and move all the US to a different frequency band. Remember the chart I have where 3.5 gigahertz would be used as a capacity booster. So these guys could go to the 700 megahertz spectrum. It could go to a 1.9, some other macro layer frequency that's available at that place. So we definitely need some sort of information from from the incumbent system to, I think LTE can, there's many bright people working on, EICIC and other methods to cancel interference in the LTE network. We just need some, and we are facing the same problem. Chris can probably confirm that, in the SysMac working groups who are dealing with, government system in 1.7 gigahertz band, we have the same problem because some information are classified, so we don't really have visibility on how the systems perform. But if we can have at least some characteristics, that would definitely, LTE side, LTE has already many features that could be leveraged to mitigate interference.
Okay. What I'd like to do is bring up another topic that was touched on, I think, by a couple of speakers, but on power. Power limitations, power levels. The NPRM sought comment on this. What are the views about how fixed or dynamic power levels can be in this band and the impact on spectral efficiency, since that's one of the issues that that drives coverage and capacity?
Well, I'll kick that off because that chart that I had in my deck that showed population density, if you sort of step back and recognize that all the infrastructure that we're talking about today really, at least in the U.S., is focused on enabling a broadband access of one form or another. It's important to recognize that not all of the U.S. is in the top 50 NFL markets. And it's important to recognize that rules can be, adjusted, especially if you have a database involved to control, and you're willing to have professional installation of equipment. And if you can imagine higher power in rural places that creates better coverage at a lower cost, that's a great thing. Just the same way as lower power in dense urban environments are required so you get better in-building spectral reuse, things like that. So power is something that should be able to be flexible within the realm of, again, just architectures and how much coverage area you have.
Other views?
I agree with that. I think as long as we have the flexibility to manage the power, I think that's the important aspect of it. And I haven't gone through to do specific power recommendations for 3.5, but rather have thought about it on a philosophical basis. In that, particularly in the early rollout, I think it's nice to have the flexibility to have higher rather than lower power systems to help jumpstart the market.
And I should also add, tier one, the people who are really incumbents and that are worried about interference, the fact that there's a database involved, the fact that there's potential for innovative spectrum management or interference management, really, mechanisms like our organization, we've talked about beacon mechanisms. If you had a beacon mechanism in San Diego when one of those boats was coming in, to warn people, to have, if you will, automatic channel switch, things like that. There are mechanisms that are important in the context of power, and you add beacons and databases together, there's some pretty innovative things you can start to do.
Are there similarities or differences between these technologies in dealing with the security issue of handling and accommodating rogue devices or other type problems that could exacerbate the interference issues with incumbents?
I think some of the answers that you heard are more appropriate for a licensed environment. If you have unlicensed or lightly licensed, I think going high power can create problems for your neighbors. And I think a lot of the spectrum exhaust discussion we have in the U.S. is around more densely populated areas. So I think you have to be careful about larger, higher power levels for this type of a band, especially if you're unlicensed or lightly licensed.
I'd add to that if you look back at the 3650 band proceeding that the Commission went through in the rulemaking that has created a lot of radio systems that are deployed, the reality is that light licensing and being able to sort of have predictability in power is probably pretty important. It's also pretty important to play nice with others that are adjacent channel and have out-of-band emissions, and that also should be taken into account when you're doing this stuff.
Dave, I wanted to ask you a question about using this for healthcare environments and for other critical access facilities. Given everything we've heard right here, do you think using current technology it's possible to provide these high quality services in a spectrally shared environment with other services in the area on a micro targeted basis, perhaps?
Sure. I mean, in the general case, yes. As long as you have the database protections, the priority access, and the appropriate interference protection parameters. Most of these networks are small area networks, so really you can coexist. I mean, you think about a hospital environment, typically indoors, typically somewhat isolated or very well isolated from other, say, like consumer uses in homes or apartments. So I think it's possible. That'll be the challenge is rolling all this out, but I think the technology is there.
Jeff?
Yeah, I think the hospital environment is really the most interesting environment. It's a fascinating environment. When you think about the hospital room of the future, how within a small patient's room there could be dozens and dozens of wireless devices. Now, are all of them going to try to seek access to the ISM band, and then what happens there? I think we have no alternative but actually to look at spectrum sharing to broaden the amount of spectrum that can be serviced in a hospital. And I think that we may end up having to do almost like an in-building spectrum management, like we see with WhiteSpace databases now, but there would have to be a spectrum manager within this very dense hospital environment. So I think spectrum sharing is actually going to improve the reliability of these systems.
And Prakash or Chris, do you guys have a view on this one?
Again, going back to my previous comment about knowing a bit more about the incumbents, I think similar comments apply here. I mean, we would like to understand what are the applications that the critical users, as defined in the NPRM, would be using that spectrum for. Again, that will help us on the operator side to coexist with not just the incumbent but also the critical users. And definitely, inside the building, there's the building penetration loss, maybe around 15, 20 dB, that can help with isolating the different small cells from each other. And again, there are other mechanisms around SON that I mentioned that could help manage interference between the different networks. And just going back to, I think you asked a question about security. Again, if we can somehow have a link between the database and then the LTE network, that would definitely help us in managing interference with the incumbents. But again, I think that link will need to be secured for obvious reasons, and I'm not sure to what extent this is taken care of in the standard. But this is something we need to look into, and how to make the link secure between the incumbent side and the operator side, for instance. And then going back to the other question about the power. I think I agree with all the panelists here that we need some flexibility in terms of the power. I don't think we need to limit the power on the lower side, but probably on the upper side.
We have an audience question related to power. How would the database know how much to lower the power, and how does it account for degradation due to terrain?
I would just mention that when we say database, what we're really talking about is a registration system. If you're an independent operator, like some of my colleagues, you're going to have to go through a registration process. There's going to be information about where you're deploying, and to sort of jump back to Amendment Y, mobile mobile stations and enabling a mobile station to be able to put energy on the air was part of that Amendment Y standard. The idea being that if you didn't get an enabling signal, you wouldn't be allowed to put energy on the air. The database and the registration system and the process that an operator goes through would actually be able to handle some of that. In other words, if you were out in a rural place, you could have one set of rules because the database would be there to validate and verify it. Then it becomes a question of, how does that operator get authorized to place that piece of equipment, and do you believe them? And that's a whole other issue.
One other thing to add is that databases in TV whitespace today actually do use terrain data just in a fairly coarse fashion to compute height above average terrains, but they do have detailed terrain data and can do detailed propagation computations.
I would like to add that these problems and a lot of others could be solved by licensing the spectrum.
So, to follow on that, another audience question, how concerned are you about exclusion zones, given that they cover large urban centers, and what solutions do you see working?
All I can say is you should look at the WhiteSpace Alliance's filing in the 3550 docket. I think that there are ways to modernize the exclusion zone. I'll just leave it at that.
Leo?
Come on, we're not going to use the exclusion zones that were put out there that exclude 60% of the U.S., so that's a non-starter. I mean, we don't need to have this panel if that's the answer, right? So we talk about reducing the power level in database lookups. That's the answer.
Yeah, as I said, if we can get some characteristics of the incumbent, on the LTE side, we can definitely adjust to prevent interference to the incumbent. I mean, and if we cannot, we can always go to a different frequency. I mean, if the radar shows up and say, you just need to turn off the network, of course, the other network will be congested, but that's also a solution. And I think, in the second panel today, hopefully we'll hear about some of the different innovative mechanisms that can be used for that, especially around authorized shared access.
If I could add one thing that I think is being we overlook. I mean, all of us in here are really spectrum experts or RF engineers and the like. But a lot of this issue is going to actually boil down to kind of deployment into facilities that you're working at. And I want to give the example for folks who are from used to DC, going to the Nats Stadium, because that's where you think this is a very good example of a heterogeneous network could be deployed. You would think 3.5 gigahertz, okay, we can provide good, ubiquitous, high-speed broadband coverage in Nats Stadium. Nats has Wi-Fi that gets very slowed down and stuff like that. And Lord help you if you try to watch MLB.com on your smartphone while you're at the stadium so you can see other games, stuff like that. But so you think you have this deployment. Well, so doing the couple hundred feet walk from the Navy Yard station to your seat inside a Nats Stadium, you're going to walk through, you're going to leave the Navy Yard station, so that's WMATA's jurisdiction. So if it's an operator, let's say, has all these great small cells they get from NSN, they're ready to deploy, you have to work a deal with WMATA to try to get in there. Lord help you trying to do that. Then you're walking on Half Street, which is a couple hundred feet. That's the District of Columbia and the District of Columbia government. You have to find a way to put up these small cells and find locations and the like. And you have to work with the tenants who have the property along the line. Then you get into Nats Stadium, and you have to work with the Nats Stadium folks and the owners of the stadium to get an agreement to deploy these cells. Well, so we think about it, well, okay, you can work all that. Well, that's a lot of hassle, a lot of logistical work, and that's going to go in and really affect the deployment and the use of these cells. And so I think that needs to be considered. So the greater degree of complexity we have in the spectrum issues, it's going to slow deployments down. And then you just have to keep in mind that there's other realistic deployment issues you have to deal with in terms of siting and the like.
We're starting to run a little short on time. There's one audience question I'd like to ask, and I've got an adder to it, and then a follow-on here from Paul. Can the panelists elaborate on how LTE can better accommodate incumbent systems, such as 1.7 gigahertz? And what I'd like to add to that in terms of the advancements in the technologies of LTE and or Wi-Fi with carrier aggregation, how might that play with 3.5 gigahertz?
Yeah, I mean, again, it goes back to what I was saying. With carrier aggregation, you could have a combination of 1.7 gigahertz band, for instance, where there are government systems, and then you could have other spectrum that the operator can have, and all of this is a big pipe. And then when the incumbent need that spectrum, for example, then you can hand over all of the users on the other spectrum, or you could turn off the carrier on the 1.7, for instance, and leave the carrier on the other band. So corrugation, interband corrugation can definitely help mitigate some of the issues. But that would be, I think, like 1.7, that's an uplink issue. We don't see devices with uplink corrugation before 2015. We already have corrugation in the downlink, but 1.7 specifically, that would be 2015 and beyond. So that could be something that definitely could be done. So what I was saying, there are different features and mechanism in LTE that would allow coexistence with different systems.
So I have to add one quick concept in answer to the question that was just asked. And it has to do with just talking about a television whitespace database that's managing TV whitespace devices, and maybe the database that will eventually be set up for 3550. If you can imagine that scenario of building flexibility based on the databases controlling how things coexist. I'm not saying that 1.7 gig should be in the database. I'm just saying that databases are going to be a great hub of the wheel for creating coexistence, and maybe that's an answer in the future.
Yeah, and I would add, I think one major issue we're facing is that when dealing with these issues, we're still, thinking, in the old days, all we are doing is looking at exclusion zones, which is basically a static way of managing the interference. We're saying, okay, you have an incumbent here, you draw a circle around it, and, you cannot go in. But, if an incumbent is only using the spectrum 2 hours, every week or every 2 weeks, the operators could use the spectrum the rest of the time. And when they need this, when incumbent need the spectrum, we can give them the spectrum back to them for, when they need that. So that's the drastic way of managing the interference. But just drawing, that's some of the issues we are facing on the CISMA groups. We are coming up with exclusion zones of 400 kilometers for devices interfering with, air combat training systems, flying over our head. I don't know how often they train in those zones, but for the rest of the time, why can't we have access to that spectrum?
Okay, do you want to Well, thank you. Not to put everybody on the spot, or maybe a little bit here. Do any of you have plans for developments of test beds or test cities as envisioned by the PCAST report, where small cell technologies and deployments can be set forth? I know we heard a little bit about that from Prakash earlier, but something more in depth for the 3.5 gigahertz band.
We're actually looking at a couple different opportunities in that space yet. It's still early to say exactly which way we're going to go, but we are definitely interested in that, in test beds.
From our side also, we are looking at a couple of opportunities, especially on 3.5 gigahertz. One issue we have is, obviously devices availability for that band. We do have a standards, but not the devices. So we are looking at different options, maybe looking at backhaul initially for that band, and then moving to access, down the way. So, and we hope that FCC will do the right thing, and everyone will, get excited and start developing devices for that band, so that we can use that for the test bed. So.
Certainly, we have a lot of interest in the test bed issue, and we're a university. We don't have a whole lot of money, and the way that we have started down this road is looking at how we might be able to modify some commercial off-the-shelf equipment for experimentation within the 3.5 band. And I've been also talking with the Navy, and we're actually working with the Navy on doing some experiments to help facilitate this. And I think we have some good ideas on how to do this in a cost-effective way.
I'll just add that it would be fantastic to, instead of like many of our potential members and users of the television band, instead of deploying TV band spectrum test beds and pilots overseas, I'd love to do it here and in a TV band context. Now that the database has been approved nationwide for television spectrum or TV band spectrum, that's probably what should happen as well for 3550. And then I will guarantee you that if there's an availability for general access tier, that the independent operator community, especially in a rural context, will, if there's no barrier there for STAs or experimental licenses, they will absolutely jump in on that band, and they have the ability to homebrew and create solutions in rural context.
Yeah, maybe I have a question for FCC. So, how can FCC, help, in that framework? Because, looking at Europe, for instance, there's, funding, not necessarily funding. I'm not talking about funding here in the U.S., but in Europe, we're looking at like spectrum sharing in some countries, and like the government in helping in many ways to do that. So, I guess my question to you: how can FCC help develop those test beds?
Come on in with a plan, and we'll talk to you.
Okay, so we'll talk tomorrow.
Just make sure you authorize 3550 as quickly as possible on those databases. That would be a really easy way to do it.
Well, I just want to thank everybody. I think we're about out of time here, so thank you for your contributions. I think this was a great panel, and I hope everybody sticks around for the rest of the day because we have some other fantastic programs coming up.
So now we're going to set up real quick. We're going to do a little informal fireside chat with John Leibovitz, who's the Deputy Chief of the Wireless Bureau here at the FCC, and a couple guest speakers. So if you want to start coming towards the front. So at the end of this panel, the chairman will be coming to give a few brief remarks right before we break for lunch, okay?
Well, good morning, everyone. Thanks for coming out. It seems like we got a good turnout. And I think the turnout in part reflects, interest in this band and getting more spectrum online. But I think more than that, I think what we're starting to hear from, some of the panelists already, and hopefully in the afternoon, is that this band in some ways is a beachhead for thinking about spectrum management in the future, thinking about, ways to sort of dramatically re-architect networks in the future, and it's very exciting. So. I think we're in a process, midway in a process where there's going to be a lot of creative ideas, and we're going to have to sort through them and try to do it in a way that doesn't take forever but moves along, and so that's what we're trying to do at the FCC. I've got the pleasure of introducing three very distinguished guests, all of whom have had, whether you may realize it or not, a very influential role in the proceeding that's underway now at the FCC. And are continue to be involved in various ways. And so let me just quickly introduce them. We've got from closest to me to farthest to me, Tom Power, who is the Deputy Chief Technologist in the White House in charge of telecommunication policy, and has been following these issues very closely. Peter Tenhua is the wireless advisor for Larry Strickling at NTIA, and obviously is one of our key points of contact as we interface with the federal users of the spectrum who use it today. And Mark Gornberg is, I think, fair to say, the principal architect, convener, committee leader of the PCAST report. He's a member of the President's Council of Advisors on Science and Technology and headed the committee that drafted the report, which was, as you've heard, very instrumental in sort of motivating a lot of the discussion we're having today. So I think the goal here is just to kind of give people some sense of some of the larger policy issues that have kind of informed our proceeding and continue to, and talk about some of the bigger topics. So I wanted to start with a question to the group about, looking at this from maybe the biggest perspective of all, what is the opportunity upside to America if we can figure out a workable sharing framework for 3.5 gigahertz? And what do you see as the risks if we don't figure it out?
Sure. I see it. And first, John, thank you very much for having me here, and thanks to Julie and the rest of the folks here. Great timing on an important issue. We look at it as much more than 3.5 or even spectrum. I mean, it's the economy. this has been a great area for America to show its leadership. You look at the fact that something like 2/3 of the world's 4G subscribers live in the U.S., leadership in things like operating systems, apps, the contribution to GDP. It's a great shining part of our economy, and we need to keep it there. And I think whether you're talking about sharing in the 3.5 band or any other aspect of spectrum policy, we need to keep growing and building on our leadership. As the PCAST pointed out, at some point, spectrum is a finite resource, and we have to be pursuing every possible option to make sure it continues to contribute both on the commercial side, but also for the government users who are also making new and innovative uses in ways that are doing great things for the country.
Peter? Nothing on risks.
Do you want to talk about the risks?
No.
You get risk.
What he said. Right.
Well, the risk is the opposite of all that, right? The
right.
risk is receding.
Right. Thanks, John, for having me. The fire's getting a little warm. Can you turn it down a little bit?
Just so people know, we were considering projecting a fireplace.
It was a good. It was a good way of attracting folks to this slot. To put the chairman, as speaking while we're and do
chairman
a little.
Is coming.
Good bait and switch. That was good move. Yeah, I definitely would agree with Tom on the upside. I mean, I'm going to borrow, Dan Lubar's slide, which I don't know where he was able to get my profile
Which one?
on the internet, because that's kind of
which one is you?
Me. That's all of me.
Oh, okay.
Right. This is the part when I started working out, and then went on a diet, and then learned how to walk. But
which part was you at the FCC, and which part was you at the TIA?
But at least we're not going backwards. That's the important thing. Is that we're evolving. We continue to evolve. That's the important thing. The risk is that we do take a step backward. So we've got evolution and advancement on a very rapid pace on the technological side, on the business model side, and the economic side. We have to keep pace on the regulatory side. So obviously the risk is that the regulatory side cannot keep up with the technical and the business side, and that's always a risk. So in the particular context of radar and comms sharing, that's been kind of going on for a while. There's several bands where federal radars and communications share frequencies. It started actually in the 902, 928 band, where you look at the allocation table, the rights are clear according to that, regulation, but technology kind of overcame things in that band, and the unlicensed actually dominates it. So you really can't call that a federal exclusive band anymore. The 5 gigahertz band obviously was very successful when the dynamic frequency selection, DFS, approach was chosen there as kind of the regulatory advancement in that band. And now this is yet another opportunity. And so I think with the risk is that we don't continue to innovate on the regulatory side.
Mark?
John, thank you. Well, first of all, let me thank the OET and the Wireless Bureau and Julie for kicking us off today, and especially the chairman's huge support for this effort, starting with the launch, before the launch, and then the launch in July, coming out front in September, and of course the vote of the commissioners that was in December that really kicked this NPRM process off. It's a real honor, first of all, to be on this panel with John and Tom and Peter, who are true public servants to this process, have dedicated their career to this process. And of course, it was quite an honor to get to chair the PCAST report. And that was really to work with about 20 experts in this area, including people in this audience today, like Jeff Reed, who you saw in the last panel, Preston Marshall, who you'll see coming up, Vanu Bose, Dale Hatfield's here, and there are probably others that are in this audience that I haven't seen in this report. John, very early on in the process, through our workings of this report, turned us onto this book that became a metaphor for the PCAST report. And this is a book that came out last year called Big Roads, and it was really on the building of the interstate highway system, which started in the, in this report in the 1930s, and then, of course, led to the systems that came in place in the 50s and had huge benefit to commerce in this country and really pushing the economy forward. We see this, our work, really built on a lot of reports that came before, and most prominently, I think, on the broadband plan that came out in 2010. And that really talked dramatically about the not only the opportunities, but also about the demand that we were about to see for mobile and for data. And if anything, the numbers in the broadband plan turned out to be conservative. So we've seen now 5 years in a row where mobile data has more than doubled every year, and there's no end in sight to what's going to happen with that. And if you play that out and say, okay, so by 2020 you might have 50 or 100 times more need for spectrum just to satisfy that, you can't do that by the current mechanisms that you have today. I mean, you can't do that by just offering more spectrum if you can offer more spectrum, and you can't do that through LTE systems, no matter how phenomenal they are and how much more efficient they have been for sharing. So you need to go to a different approach. And this is why the approach that has been talked about through the the different pieces of the PCAST report, and particularly through the start of the 3.5 as the petri dish, I would say for that, is really critical to being able to have a chance to satisfy that 50 to 100 times or more increase in demand that we're going to see for spectrum. In terms of the opportunity, I would argue that the big opportunity in the 3.5 is for it not to be a one-off. The big opportunity in the 3.5 is that we think about it holistically as the start of many bands that will follow, and that we, in our work of the 3.5, that we think that way, and not to specific pieces of the 3.5, but to the bigger picture. And that includes the start of like an air traffic control system, a spectrum access system, and all the pieces that will follow from that. But our belief is that if you put all these pieces together, you have the opportunity to create thousands of times more effective capacity. And if you can do that, you can change spectrum from being the scarce resource to an abundant resource, and then you can proliferate a whole economy on top of that. And that is the huge opportunity. And the huge threat, by the way, is that we don't do that, and somebody else does. And so we're grateful for many people that have come to support the PCAST report, which, by the way, really started to build on the FCC WhiteSpace work. But the people like the Europeans also picked up on the report. And so on September 4th, the European Commission basically came forward to the EU to say, you must implement not only that, but you should implement going beyond that for sort of all sharing. And we have other forces around the world that are building in these areas. So we have had the fortune, really in the last few years, to turn from being the laggard in this area to being the world leader in this area. But the next piece that will be critical to competition is going to be spectrum sharing. And so we have to lead in that as well.
Thank you. So turning to from the economy to sort of the government side, obviously they're not totally separate, they're related. For one thing, the government, especially in the security side, they're protecting the economy. So that's important to note. But Peter and Tom, what do you see as the greatest areas of tension from the government perspective, and how do you think these can be resolved, as we work through this process?
It's all harmony, no tension. The key tension is going to be, well, what's in it for the federal side, right? It all goes down to incentives. Monetary incentives are fine, and there's laws that require the reimbursement for costs involving sharing in some cases and relocation in other cases, and that provides some incentives. But there's also incentives for access to the spectrum in new and different ways, just like the non-federal side gets. There's incentives from being able to upgrade radar systems, or make them more efficient. There's incentives that are created from having access to the new technologies, and I'll put a plug in for John Chapin's project and Spark at DARPA that Tom and Assistant Secretary Strickling did regarding a blog post that came out Monday, right? And that highlights that program. So those are the drivers, I think, in what makes the federal agencies want to come to the table. But they need to come to the table and participate and have be part of the collaborative effort in developing kind of the rules of the game, and how they share, how the tiers are defined, how the rights are defined, and most importantly probably, how those rights are enforced and protected.
I would also say some of this comes down to some really kind of nitty-gritty practical stuff. As the federal agencies are used to sharing with each other quite a bit, but sharing with the commercial side is new, and so they're working through some just practical problems. They're first worried about protecting their systems. That doesn't just mean not the risk of sharing. It also means thinking through how do we share data about the systems? How do we share access to facilities when industry wants to come in and do testing and monitoring near federal facilities? How do we make sure that information is shared but is secured? Issues like liability, things that the lawyers in the room deal with, in all sorts of contexts. We've worked through, the government works through these things in all sorts of different contexts, but it's new in this context, and so it's just some nitty-gritty hard work to even sit down and get the engineers in the room who can start working with the data. The industry, came to the FCC last year. Got a special temporary authority to do this testing, but what has slowed it down is just some of these nitty-gritty issues. But I think that's the kind of thing that is not going to be unusual as we sort of embark on a new chapter of spectrum policy. And it can be frustrating as all get out for folks on both sides, but it's just the kind of thing we got to work through.
Okay. Maybe we could start with the next question. Start with Mark. But how do you respond to people that say that the focus on sharing is diverting attention from clearing and reallocating spectrum?
I think they are not mutually exclusive. I look at this as in terms of clearing today. There's a debate going on, for example, in the 1755 to 1780 band, and the NTIA report came out in March, and that report said that that's 10 plus years, $18 billion, extremely disruptive. People will try to figure out a way to whether they can go to cleared, shared, or whether they can find some middle ground. And then there are a lot of groups that are working on that. We focused much more in our report on what I would call the higher frequencies to start with. We looked at 2700 to 3700, areas that really were not, areas that you could easily clear, and said, okay, there must be a different way to go about that. There must be a way to use small cells. There must be a way to use systems and make that very effective spectrum. But I would also make the argument that the sharing and clearing are not mutually exclusive, because the best way to get to cleared spectrum is probably to start to look at sharing and try to figure out how to thaw those systems so they're more flexible, so they're more easily movable. So today, if you look at that NTI report, that would say, okay, start the process towards clearing and work towards 10 years and hope to have that spectrum available. We look through our report as a pragmatic way to try to get spectrum to people, let's say, in 3 years through a sharing mechanism. But as those systems get more flexible, that spectrum will become not just more shareable, but effectively come closer to look like cleared spectrum. So I think they work together. And actually, that's why that's a very good solution.
And I had a couple things. I agree with everything Mark said. They do work together. When we talk about in the 1755 band clearing and what NTIA concluded would take 10 years and $18 billion, even that wasn't actually total clearing. There were still going to be some systems left behind. So even when we say clearing, we're actually talking about still some sharing. And I think as technology develops, you'll see more and more of that sort of integration. The two concepts kind of blend together. The other thing I would say is, of course, I think in an ideal world, anybody who's a user is going to want to have exclusive right to their spectrum, just like any other asset or toy. You want even when we're kids, right? Sharing is not exactly the thing you jump to, even though mom is telling you to share with your brother. When folks, I hear a lot of calls for clearing. They just need to clear. They just need to clear. Well, if you subscribe to that, that's still only half the answer, because for federal systems that still need spectrum, where do they go? And that I don't often hear that half of the solution when people push clearing. And my analogy is to if I decide that schoolrooms, classrooms are overcrowded, well, what's the solution? Well, kick all the kids out. You've cured it, right? But what about the kids, right? They were in the classroom for a reason, and the federal systems are using spectrum for a reason. And I think that part of the equation sometimes gets overlooked. Certainly not ruling out, as Mark says, as we examine sharing opportunities, we may actually find, what, we can clear out of here. It's a very similar examination. So I don't rule that out, but I do think folks need to realize you can't just say clearing as if federal systems don't need to operate anymore.
And of course, I think one thing that is worth pointing out is all the spectrum at some level is shared today. In certain places there's a radio quiet zone, for example. So there is some level of geographic sharing going on in all the bands. I think obviously that's a sort of a place where there's not a lot of use, so it's a lot easier. But it may be a existence proof. My 2-year-old loves to share his toy.
I was brought up differently.
Yeah, okay.
Peter has a picture of me.
I was kidding. He doesn't want to share his toy. Well, maybe directing the next question to Peter. A lot of the discussion today, especially, but in the I think in this sharing around the sharing construct more generally, focuses on technology and what technology can do. But of course, there's a sort of a legal and regulatory environment in which this technology operates. What do you see in the way of changes that need to happen to that kind of legal regulatory framework for the technology to realize its full benefits?
Well, as I mentioned before, I mean the risk is that the regulatory constructs will crumble under new technologies. Evolution, and we need to avoid that. So what has, at least in the last few years of my career, I've noticed a necessity, and I'm from Missouri, so show me is our motto, and that's what it takes. It takes the technology people to show those on the other side of that table on the regulatory thing to say, no, we can agree to remove regulatory barriers and share the spectrum because look what my technology can do. And programs like Spark, XG, other programs, the test bed, the stuff going on in the 1755 band, those are all efforts basically for the commercial side to not only, reach out to a very large segment, market segment, which is the federal side of spectrum users, and potential customers, hint, hint. But they provide a proving ground. You need, like the WhiteSpaces. The WhiteSpace database provide a proving ground for this. So take advantage of that. Demonstrate that to federal users and see how then they can gain trust and confidence, which is, by the way, not going to be enough because they're going to want to see the reliability in the way these systems operate. So really the opportunity is to take advantage of the development that's going on now in all the across these various bands so that the sharing that has been going on actually since the beginning of time, when the telegraph operators used to have to stay off of the air for a certain amount of time to let the ships, do their distress calls just in case. That's been going on. It just has evolved into the more dynamic sharing, which is going to be database control. It's going to be a combination. It's going to be all kinds of different type of sharing approaches, but it's going to be on a more dynamic basis. But technology is going to drive it, and the regulations will then provide that flexibility to let that technology evolve, and the business models along with that, and then the customer base can be as broad as it possibly could be, from the equipment side.
We have a question from the audience, from an eminent member. Well, can I say who it is? From Dale Hatfield. So, it's actually a very good question. Not surprisingly, coming from Dale. So a lot of people have focused on the importance of incentives and getting the incentives right if sharing is really going to become the norm and the rule in the future. Do you think that the incentives are strong enough to promote adoption of sharing both for federal and non-federal spectrum?
Are incentives today for agencies strong enough?
I think for stakeholders in general, maybe it's another way of questioning is how do we think about the incentives of the different people who are at the table in this discussion?
Sort of following up on what Peter was saying, from our side, there's this kind of delicate dance we have to play because, we don't want to be prescribing specific approaches or specific technologies or specific architectures that, what do we know, right? I mean, we can make an educated guess, but we as the government don't want to be overly prescriptive. On the other hand, we do need to allow the market and allow engineers and business people the freedom and flexibility to pursue what is going to work in the marketplace. So, at the end of the day, I think the incentives the incentives are good in the way that the market forces are always good incentives. The invisible hand is going to push this, and I think the government's challenge is simply to make sure that we can accommodate and leave room open for those kind of for the invisible hand to push its way along. But you can run into interesting situations. The more we pursue, let's say, clearing, if we were to say that that's all we believe in, well, the money to invest in new sharing technology is going to stay on the sidelines. And so, we want to pull that money in without, dictating that there's only one or two approaches.
Just to enlarge, and I think maybe we should have Dale up here to answer his own question too. But I think the development of and the encouragement of collaborative multi-stakeholder approaches may be one of those mechanisms for the various stakeholders to understand the incentives on each side, and what drives, what are their mission capabilities, what are their demands, right? If they're kept separate, and you have regulators basically mediating for them, I think you lose the value of the information that can be gained at those tables, and so that kind of then creates the question of kind of who should be there, when kind of does it need to be kicked off, and under what kind of organizational structure. Sometimes it's under industry organizations or things like the BTAC that Dale help get start. I mean, there's a lot of interesting. The internet basically got started that way, right, and evolved that way. So the more and more we can bring the stakeholders in, I believe, into the table, the more we can understand what drives them, right, and what are their fears, what are the things. And then you say, oh, I got a solution to that, and they can work things out, together in a more collaborative effort. And I think just one more thing about incentives is that it's the public interest that we all kind of work for, is our incentive. We like to see the public get greater access to bandwidth. We like to see soldiers be able to train like they fight. We like to see planes land safely and fires get put out. So that's great, but everybody else are more self-interested, right? We have to understand that's what their incentive is, what are their self-interest. So it's all about exchanging that information. Here's my self-interest. Here's mine, and then us to basically figure out, well, where there's a conflict, that's for us to kind of step in.
So Dale's exactly right that one of the biggest challenges in all this is to create incentives on both sides to want to move forward. It's not really the technology so much. The technology is here today that can easily be evolved to do this. It's really the motivation to want to do this. On the commercial side, I would argue the incentive is making spectrum available and putting a harness in place to be able to start to use it. We've never had a case where when spectrum's been offered, there hasn't been immediate uptake of that spectrum. And unlicensed is probably the best example of how that spectrum was used immediately when people had no expectation that use would happen. And now you have the opportunity to have a higher quality of service system to create quality of service spectrum. So I think the incentive on the commercial side will be the simplest. It's there. We'll use it. As people build devices, it'll have a virtuous cycle. It'll really start to take off. The federal side is probably a lot tougher to figure out an incentive system for the agencies. And we speculated on one in the PCAST report, which is the notion of creating a spectrum currency, and whether it's exactly that or something close to it. But it was the idea really of incentivizing the early adopter agencies to want to make their systems more flexible, make them more shareable, be more mentally in the zone of wanting to share, and make that available for commercial use. And so what we said was the Council of Economic Advisors, the OMB, should get together, figure out a system to start to work with the agencies on their plans so that as people lowered their spectrum footprint and made the forecast and made the commitment to lower their spectrum footprint, if they did that earlier, they would be recognized for that and basically be rewarded somehow for that early work. And so in concert with that, we thought one of our most important recommendations, which is really under congressional control, is to change the Spectrum Relocation Fund to a Spectrum Efficiency Fund, where today people, as you gather money for auctions, that money can only go back to folks that are basically moving their systems or at least making them more efficient within that specific band. If you think about this beyond bands, which is really where I think sharing takes us, then you need to not only reward people for making their systems more efficient rather than just move them, you also need to reward people for making them more efficient if they're not exactly in the band that collected the income to get reimbursed. And so we think that mechanism, if Congress changed that mechanism and you put a system in place of some kind to reward the early adopters and they could get that money for making their systems more efficient, well, hopefully that's a carrot that is sort of the opposite of spectrum fees, which Europe has tried. But that becomes a carrot for an incentive with the agencies. And the early ones get rewarded, and the laggards basically have to figure out how to do that within their own budgets unless more money is available.
It's the PCAST, did a lot of great thinking on this, and a lot of us have wrestled with it. And you look at what we're doing with the reverse auctions with broadcasters. It's the same thing. It's offer them some compensation and let them figure out what the right answer is, and that's the same thing with the agencies. There is pushback on it. The idea of sort of effectively recognizing an interest that the agency has in spectrum is kind of a new concept and could create perverse incentives if you don't do it right in terms of actually giving agencies incentives to take more spectrum so that they can then benefit when they give it back.
I think the chairman's on his way, so I'll ask one last question. 1,000 megahertz. So the PCAST report talks about 1,000 megahertz. I think Mark, you mentioned the specific recommendation, which was 2.7 to 3.7. How do you see the prospects for 1,000 megahertz of shared spectrum?
I guess I think why stop there? Actually, the ultimate goal is to wring every last unit of productivity out of all the spectrum. So there will no doubt remain exclusive allocations on both the commercial and federal side. But we should always be looking to squeeze more out, and where that means sharing, that's what we should be doing.
Well, it depends who you ask and how they define quote-unquote sharing. Some will say that, well, all the cellular networks are shared, right? Or the spectrum in this, all the commercial spectrum shared amongst all us subscribers, right? But if we're talking about, distinct, unaffiliated, systems that are using the same frequency in the same place at the same time, that's, I guess, the ultimate goal, right? Is that, and that's going to take some technological miracles, right, John? I'm talking about the exact same, like, millisecond.
What do you see as the prospects for other parts of the radar bands that that sort of nearby?
Well, radars and communications are two completely different applications. But I think the DARPA project is going to try to evaluate is how can they complement each other, in the sense of how can they first let's see if they can communicate with each other, and let one system know what the other system's doing for the first time ever, just like the WhiteSpace database allows the wireless microphone folks to say to the WhiteSpace users, here's what my plans are. So the more real time, close to real time you can get, the better. If there's a way that you can use a radar signal to actually do communications, I don't know if anybody's going to be proposing that, but I think what it requires is collaboration among two very distinct parts of industry that I don't think cross paths ever. Those that serve the DoD and the federal side, and those that serve the commercial side. On a lot of DoD vendors do both communications and radar, but even within those companies, not sure if those communications segments are talking to the radar segments. It'd be nice to maybe see some joint venturing among, the folks that normally supply, Wi-Fi devices or commercial, carriers, and the ones that supply the federal side. I'd like to see them, collaborate on some of these systems.
Maybe Mark, I'll give you one more question, different question for the last question. In 50 years, is FCC going to stand for Federal Communications Cloud? Or are we going to be reduced to a database?
Well, 50 years from now, the hope would be that systems are all flexible enough. You'll have a computer system, and every year you'll hit a button and you'll scramble the allocations and basically make it more and more efficient and make it more and more shareable. So, John, you'll have some system that you'll be able to use, and you'll do brilliant work basically in that every year. And I think a lot of this will come down to, of course, how industry evolves to live on top of this innovation cycle. We looked at support from the Wireless Innovation Forum, from the WSA earlier. There's a great blog post in early September by Dean Brenner of Qualcomm that talked about sort of new devices that can come forward, particularly in TDE, LTE, TDE. I think or TDE, LTE. I think that all of this will give you the system that you need to be able to do this so easily.
So I take from that the solution to our long-term solution to our budget problems of the FCC is to turn us into algorithms, and hopefully I think there's a lot of R&D to do before that. So I think our job is safe for the next 50 years. I wanted to thank the panel. Obviously, especially Mark came long distance to be here, and I think the chairman's on his way. So maybe people can just kind of stay put and move on to the next segment.
So I wanted to just real briefly let you know we're going to break for lunch right after the chairman gives his remarks. There's a couple that we have a cafeteria here in the commission, and then if you go out the main doors where you came in and turn left and go up to the corner and then turn left again, there's a couple of cafeterias. There's a deli at the corner, there's a Potbelly, there's a Starbucks. So we're going to have lunch from 12 to 1. If you want to stay here at the commission, we have a couple of staff over here, if you guys can raise your hands real quick, that can take you down to the courtyard cafeteria, and then we'll be back there about 10 of 1 or so to bring you back here in case you can't get through security or don't know quite where you're going yet in the maze of our hallways here at the commission.
Extending the reply comment deadline in this proceeding to April 5th, and the reason for doing that was we wanted to allow for today's insights to kind of inform the record and also hopefully inform the reply comments. So hopefully people in their reply comments will take stock of some of the things they're hearing today and respond to them. We're going to put the presentations from today and I think even the transcript of today's, maybe the transcript. We're going to put the. I don't think this part needs to be in the transcript. We're going to try to put as much of today's discussion into the record as we can, so that it can actually inform our decision making in the rulemaking from a legal standpoint. So people should hopefully engage with the material here today, but also with each other informally. The other goal is to get people together in the same room so you can talk, and hopefully some new ideas will come out of this.
So it is my great privilege and honor to introduce our chairman, Julius Janikowski. Under his leadership and with the collaboration of the other commissioners, the commission is focused on unleashing opportunities for wired and wireless broadband. And since time is short, I'm going to turn the podium over to him.
Hey, Mark. Thank you, everyone. I apologize for running late, but I absolutely wanted to be here. One, to thank everyone who worked on today's agenda. Where's John Leibowitz? And there. All right, good. And not to single anyone out, a lot of people have worked on it. To thank the people who were on the first panel. I see Tom Power and Mark Gorenberg, and was Peter Tenhula on the first panel? Thank you very much. Here's why I think this is such a big deal. The panel this morning on small cells and 3.5, and the panel this afternoon on spectrum sharing. This is a very sophisticated audience, and you understand, the challenges and opportunities that we face in the spectrum area. And it's not news to people who've been following us for a long time. But let me put it in a larger frame. The opportunities around mobile are really endless, right? We see what's happening in our own lives with smartphones and tablets. The data keeps coming in on the positive effect on our economy. The level of wireless capex that we're seeing in the U.S., very high on absolute terms, $35 billion this year, increased annual capex by 40% if you measure the annual numbers over the last 4 years. Very big on an absolute basis, and really impressive on a comparative basis. Right? Europe flat in this period. Asia close to flat in this period. The U.S. investing more in infrastructure than China in this period in terms of year-over-year growth. These are all big deals. And the other thing that we're seeing in mobile is this dramatic uptick in innovation on the platform in the last 4 years. Just think about it. I mean, everything that we do on our smartphones and tablets, we weren't doing 4 years ago. The apps economy barely existed 4 years ago. The tablet didn't exist 4 years ago. It's an amazing thing, but of course it's presenting these massive challenges around all of the demand for spectrum that the devices are using. And so if we think about the effect on our economy, if we think about the ways it can transform education, the ways it can transform healthcare, the ways it can transform all the major verticals of importance to our economy. It's just amazing. This you all know. And you also know this, but it's worth being a little bit explicit about it. In the last 30 years, there were two major spectrum policy innovations that had tremendous benefit for our economy and society. And everyone here knows what they are. One was auctions of spectrum for flexible use. We're so used to it now that we think that it's been here since the beginning of the SEC, but of course it's not the case. And until 1997, is that when the first auction was? 6? 94? No, 94? Until then, spectrum was distributed through comparative hearings and lotteries, and generally for very concrete, specific uses. And auctions have been a tremendous vehicle for allocating capital, for attracting capital, an amazing success, and it comes out of a policy idea. And the second major policy innovation of the last 30 years has been unlicensed. Right? Let's take some spectrum, set it aside for unlicensed use, and the truth is, and see what happens. And of course, what happened was, garage door openers, but Bluetooth and cordless phones, and of course Wi-Fi, adding tremendous value to our lives, tremendous value to our economy. The challenge that we started talking about at the Commission 3 years ago was not just how do we solve the spectrum crunch, but it was also how do we develop and move forward on the next generation of big spectrum policy ideas. Because it just can't be that auctions and the kind of unlicensed we have are the last two big ideas we'll have in spectrum policy forever. And what's happened over the last few years, thanks to the work of many people in this room, inside and outside the agency, is there are now, I would say, three big ideas that are being pursued in a forward-leaning, aggressive way, each of which has the potential to become a major spectrum policy innovation that we'll look back on and say, yes, that was the next chapter of the story, or those were the next chapters of the story. And, what are they? One is incentive auctions, and I don't think that's the subject of today's sessions, but obviously they're a big deal. Congress has passed the law. The FCC is moving forward speedily on implementation. Very big idea to use market-based auction mechanisms to reallocate commercial spectrum for less efficient uses to flexible use. The other two big ideas include a next generation of unlicensed and spectrum sharing between government and commercial. And so what's happening today is very important because it's a very important part of our process to advance all of this agenda. So one, when you think about 3.5 gigahertz, an incredible opportunity to free up 100 megahertz to address the spectrum crunch, because of course incentive auctions can't be the only thing we do to just free up more spectrum. There's great, very healthy discussion about the best way to free up 3.5 and the best way to get it on the market. The one thing that I can tell you the FCC is committed to is getting that 100 megahertz and 3.5 on the market and doing it in a way that reflects the best thinking and the best ideas and the most value we can unlock for our economy and society. Small cell revolution is an unbelievably big idea, and so the insight of thinking about 3.5 as a small cell band and what that can mean for moving forward on it sooner rather than later, very exciting. And spectrum sharing, a really exciting idea. Now, sometimes people have some concerns about spectrum sharing, and I want to address it head on. Sometimes people say, oh, when you think about federal spectrum, the idea that we would move from a clearing and reallocation model to a spectrum sharing model is not a good idea. And I think that misunderstands the goal around spectrum sharing. And let me be very explicit about this. Any time that there is federal spectrum that can be cleared and reallocated, we should do it, because we should drive the most efficient use of that spectrum. But where that's not possible, then of course we should look at spectrum sharing, because the alternative is to say, all right, it's not possible to clear and reallocate the spectrum, and therefore all of the inefficiencies should stay and be part of the landscape. Well, that doesn't make any sense. So the work that you're doing today, this morning's panel, the one that's coming up later, is really important work to move forward on these next generation spectrum policy ideas, not because we're interested in having a debating society, but because we're interested in really moving forward as an institution quickly on 3.5 gigahertz, on spectrum sharing, on the other ideas that you're talking about, and get them in the market fast. We know other countries are looking at all these ideas. We want to be first. I want to thank NTIA for working with us as partners on this. It's just so important, and we all know it will lead to a faster, more efficient resolution if that continues to happen, and I know it will. So thank you all for participating in this. You're working today on really big, important ideas for our economy, our society, for our global competitiveness. I thank you for spending so much time on this. This will very much become part not only of our record, but part of our very active thinking to move forward on all these issues quickly. So thank you very much.
All right, so we're going to get started now. So I want to thank everybody for coming back. A couple of quick reminders. If you're sitting in the audience or watching remotely, please submit your questions anytime you think of them. You don't necessarily have to wait till the end. We have staff here to collect the questions, and if you're just joining us, you can submit questions to livequestions@fcc.gov. Just email your question with your name and your company affiliation. Also, we want to remind the speakers to speak directly into the mics as much as possible. If you're turning your head to look at the moderators, they might not pick up what you're saying on the web stream. So now we're going to have the second panel, which is the Spectrum Access System, Innovative Approaches to Dynamic Spectrum Sharing. The moderators for this panel will be Mark Settle, who is the Deputy Chief of the Policy and Rules Division in the Office of Engineering and Technology here at the FCC, and Robert Soule, who is the Chief of the Spectrum Engineering Branch at NTIA's Office of Spectrum Management at the Department of Commerce.
First, I'd like to thank all the panelists for participating today as this panel explores new sharing technologies, especially as they relate to the ideas that were put forward in the PCAST report and the Spectrum Access System, as compared to some of the technologies we've developed up to date, like TV whitespaces. And also want to thank our co-moderator, Bob Soule, from NTI's Office of Spectrum Management. What we're going to do is briefly ask an opening question to each panelist, give them a short introduction right before we ask that question, and then we'll open it up to follow-up questions and also questions from the floor. So I'll ask Bob if he wants to ask the first question.
Sure. Thanks, Mark, and thanks to the FCC for having us down here again today. First question is for Peter. Peter Stanforth is the CTO and co-founder of Spectrum Bridge, which is one of the TV whitespace database administrators selected by the FCC. So, Peter, can you tell us about your experience developing access tools in the whitespaces and other contexts, and how you think that experience can lend itself to the creation of the SAS as described in the NPRM? Thank you.
Sure. So, thanks, everybody. Let's see if I can drive this thing. All right, good. So I see a lot of familiar faces here, so I'm not going to bore you with an intro to what we do. These guys said it right, that we actually we have solutions today that run secondary marketplaces for Spectrum, and we run a couple of different database solutions that acts as air traffic controllers, if you like, for sharing Spectrum. So with that said, how does that apply to what we're doing? And just quickly, some of the things that we learned. If you go back to the early days of TV whitespace, there were a lot of people who felt it could never happen, that it wouldn't work. And then there were the people that said, oh my God, how can you trust industry to do it? And then they look at us and say, what the heck does Spectrum Bridge know about this? How can you trust anyone to do it? These guys will fight with each other, they'll create a mess. And the short answer to all of that is that actually through a variety of efforts, and they were substantial in some cases, we're now at a point where people are reasonably convinced that it actually works pretty well. Some of the things that happened early on, the group of original database appointees realized that in order to comply with the rules, they actually had to do some things and that they needed to do some work. And the two things that were critical were that we all gave the same answer and that we could actually synchronize with each other. So if somebody were to register or do something on one of the database solutions, that it would actually work across all of them. And the end result was something very pleasing. I mean, our contour calculation goal was to beat the FCC's 10-meter accuracy, and we ended up probably in the order of a few centimeters over 100 kilometers. So the long and short of it is that when it was necessary and it was in their own best interest, industry could clearly solve some of those problems. And so it can work in a competitive environment. There are today 2 certified databases, and the other one's further down the panel, and there are 2 actually in certification with the FCC. So it doesn't have to be a one-size-fits-all or even a single entity that deals with this. The last thing that we learned early on, and one of the surprises to us, I guess, was that over the last year since we were certified, it turns out that some of the most active users and some of the biggest users of our solution have actually been the incumbents. The broadcasters and the microphone guys are actually using the system, not so much to find out if we're doing the right thing, but they actually realize that as the process came about of collecting this information and managing it in a dynamic and almost real-time area, there was a lot of really useful information to them. And so as you look forward to this SAS, I think one of the things we should look to is it's not just about a protection system for the incumbents. There really are potentially advantages to the incumbents that come out of this, and so we should take a look at that. The other thing that's, I think, important is that it's not just a database. I get into long philosophical arguments with John Mallier about exactly what a database is, but really the core of it is a database of who the incumbents are and how to protect them. But in actual fact, it's more than that, and it's more than we actually focused on in TV WhiteSpace, because in the rules for WhiteSpace, it was all about protecting the incumbent. But when you're sharing, it's got to be a two-way street. You've got to look at, well, just because my little 100 milliwatt device won't interfere with a megawatt TV transmitter, what's he going to do to me? Right? So you have to have a sharing in the point of view of the information. Some of that information has to go two ways. I need to know not only that I am protecting somebody and that I can, but also what their impact is going to be on me. So as we look to, the last spin up of last minute or so of what we have to do in terms of the SAS, I think one of the first things I say is that we don't need to be exactly right off the bat. One of the things that happened after we got certified was that the FCC kindly brought out a new set of rules for WhiteSpace. So we put those rules in, and did anybody notice we did it? Once you have a database system and once it's operational, to realize that you want to fine-tune, whether that's to make things more liberal or more conservative, is a pretty straightforward activity. And to most of the radios in the field, it's also a painless activity. The second thing that really is important, and it came up a couple of times this morning, is that just because in WhiteSpace we made rules that were the same everywhere, they don't have to be. I talked earlier about the accuracy that the database providers have come up with, in orders of centimeters, down to, do it by the city block, do it by the minute per day or minute per hour, do it by smaller chunks of frequency. And so just because you have a set of rules that are necessary in, say, San Diego Harbor, doesn't mean you've got to have the same set of rules in the middle of Iowa. These solutions generally are cloud-based today, so they scale very well, so that's not an issue. And another thing that comes into the reason for several database providers is when you look at all of the applications that could get deployed within this new spectrum band, not all of those solutions and not all those radios are going to need exactly the same kind of set of services. So in WhiteSpace, if I have a simple access point in my house, I want to be able to get a channel list and I'm done. If I'm a WISP deploying a county-wide network of hundreds or thousands of nodes, that's a total different set of services. And so, again, with the SAS, there isn't going to be a one-size-fits-all. So that's why the radio vendors, to wrap up, really want there to be an opportunity to have multiple of these kinds of SASs out there, because they really believe that some of them will optimize for different kinds of services and applications, and that that's the best solution for everyone. So with that, we'll move on.
Sorry. Thank you, Peter. Preston Marshall holds a joint appointment as a research professor in the Department of Electrical Engineering at the University of Southern California and division director at the USC Information Sciences Institute. Previously, he was program manager at the Defense Advanced Research Projects Agency for 7 years and developed research programs in cognitive radio, dynamic spectrum access, sensor networks, content-based and delay-tolerant networks, and probabilistic computing. Preston, you've been studying issues surrounding dynamic spectrum access for a number of years. What do you view as the benefits to the creation of a system like the SAS as recommended in the PCAST report, and what may be some of the possible pitfalls?
Okay, thank you. So I want to talk about SAS first, then we'll talk a little bit about DSA. I think we have an opportunity here with an incredible amount of convergence that this is a good idea and a lot of discussion about how to go down one of two paths. The first is to focus on just solving the 3.5 gigahertz problem. And I think that would be the tragedy. That would be the failure if we just got 3.5 out of this process with this much agreement in the room. And what I'd like to do is to argue towards the idea that what we're really doing here is beginning the process of setting up a framework for sharing the rest of the 900 megahertz that PCAST talked about. And so we ought to be thinking about two problems. What's the general framework for sharing? And what's our vision for the next 20 years of spectrum access systems? And then what are the specifics of implementing that in 3.5? But put that first question up, because that's the really important one. If we just do 100 megahertz, there's no legacy. If we set a ground rules and framework for a gigahertz, then there's a legacy that people can build on after we're done here. And after we've been written up in history and complemented by the next FCC chairman. And so I really want to think about what are the benefits of the long-term vision and what that might include. And this is really, to some extent, channeling the fireside chat and what was in the PCAST report. First, let's think a little bit about what an SAS is. When it first came out in TV whitespace, it was really focused on solving very, very specific problems in non-interference with TV receivers. But since then, we've had a lot of learning experiences. If Nextel didn't teach it to you, if the TDD issues didn't teach you, you had to be dead not to understand that Light Squared said that receivers are a bigger driver for spectrum management than transmitters. And so SAS is an opportunity to not only do frequency deconfliction, but to start to automate coexistence. Some wonderful work's been done by the CSMAC, Silicon Flatirons, and Pierre Debris' work on receiver framework and receiver visibility. This is the time to start to instantiate that into our frequency management process. We have a nice clean slate. There's nothing deployed out there. We don't necessarily want to use that lousy word receiver standards, but at least an opportunity to require visibility of receiver characteristics and make that part of the database system. So we've talked a lot about frequencies in the SAS. I believe it's important to also talk about receiver characteristics and coexistence. Secondly, most of our thinking has been passive. The framework in the TV whitespace was predicting interference. We have done prediction of interference since 1912. The SAS brings the opportunity to bring in closed loop. Ultimately, our goal for SAS should be dialogue between incumbents and sharing systems. Initially, we will use RICE and we'll use all those propagation models engineers love to fight and pick and choose to make their case before the commission. But ultimately, we'd like to use reality. So we should be thinking about an SAS whose goal is to build a closed loop between those radars, between those incumbent users, between the secondary users, and amongst the secondary users. The last one I'd like to talk about is the opportunity. Let's make sure that we leave room for our SAS users to bring in additional value services. Interference alignment jumps to mind, and I'm sure there's a lot more, and that's up to the venture community to decide. So there's a temptation here to just jump in and go do 3.5, and it's really exciting, and that's why everyone's in the room. But I think we should resist that temptation and think a lot about what is the framework we want to build. How do we do it incrementally, not necessarily as rapidly as we'd like, but to build it because our goal should be the full 1 gigahertz. White spaces should not really be something that we think about as a one-time event, that we're here to do 3.5. We're here to set up a process that over the next decade will bring more and more spectrum into white space management. And that's a much broader question, and I think somewhat beyond what a lot of the comments I've read are, but I think that's a challenge to the Commission, to pull out of all the input we've given and come up with something that really partitions it. Thinking a little bit, and there's 2 copies in here in the handout, and that's just to reiterate the point, I guess. So, what is our goal? Our goal is not to do 3.5. Our goal should be establishing the framework for SAS systems in the future. Julie sitting over there, if I had my way, if I could Vulcan mind meld to you, it would be that every paragraph in this NPRM has 2 pieces. One that says all SASs must provide this service, and then one that tailors it and says in 3.5 this means this. And then we're going to that would be point A, and we'll bring in B. If you look in a way at the Red Book by NTIA, you see that it's got this broad principle and then all of the specifics of the band. I think that approach brings us a lot. Industry can build to what an SAS is. People can build product in advance of the spectrum becoming available. I think everyone wins from that. I just wanted to do one other point. I was asked a little bit about the role of DSA in this. If you are a DSA researcher, you feel awfully left out with all the discussion of TV whitespace and databases and all. But I really think this is what DSA needed. We did DSA at DARPA doing 5 signals out of 1,000 military signals. If we go at 5 every decade, we will never get there. The databases offer the DSA community knowledge of what's going to be in that band. That makes the DSA problem much more tractable. DSA is advantageous to incumbents for the first time. We've really had no advantage to an incumbent of allowing DSA. But if they can get out of having to maintain the database, then there's an advantage to incumbents. For the first time, we have incumbent advantage in DSA. And I think this is really going to be what enables DSA to take off if it's self-defense mechanism, if it's not the total mechanism for interference avoidance. So I think we should really look that TSA is the next thing that rolls in behind the whitespace. Thank you.
Next question is for Vanu Bose. He is the president and CEO of Vano Incorporated, which uses software radio technology to solve challenging wireless coverage problems. So could you maybe explain your thoughts on how an SAS could effectively manage operations between 2 different tiers of users as proposed in the NPRM, including between indoor and outdoor users?
Sure. First, let me say that this NPRM is very exciting. When we started the company based on software radio technology in 1998, this is actually what we wanted to do. But the rules didn't allow it. So we found other uses for the technology, and I will say in the intervening 15 years, the underlying technology has improved dramatically. We now have gigahertz processors in our cell phones. We have RF CMOS devices that can tune from 100 meg to 3 gig. We have small form factor antennas. So the underlying technology has matured to the point where this is practical and cost effective. So it's a very exciting time. And let's see. So I always get uncomfortable when I find myself agreeing with everything Preston said. But I really agree with it, and I think I'm going to focus more on a couple specific examples. And I think that the overwhelming point is, look, we tend to talk about the spectrum access system as kind of a database because we started with white spaces. But a database is just a part of it. It's really an interactive management system, and the benefits of doing that are huge. So one of the things, and following up on what Preston said about DSA, is you've got to combine databases with sensing information. But by sensing information, I don't mean DSA. DSA, it's sort of a lightning rod for a lot of things. But if you step back from that, you realize that we do sensing in most of our networks today. Good old GSM cell phones, been around for 2.5 decades now. Every 480 milliseconds, they scan the surrounding and report the power levels of the nearest 6 to 8 towers. Wi-Fi scans to start up, periodically scans. It triggers scans when the interference gets high. Now, if we take that information that is being scanned anyway and bring it back to the database, now we have a much more powerful system. Because what the database gives you is sort of quasi-static global information. What sensing gives you is timely local information. You combine them both, and you can make much more intelligent, much more efficient decisions. And I'll give you 2 examples of how, by combining sensing information with the database, you can solve some problems that would be hard to solve otherwise, or you could solve them with less efficient solutions. The first is the boundary problem that was highlighted in the NPRM. How are we going to coexist if we allow the Tier 3 devices to be licensed by rule indoors and we do geographic area outdoor licenses? What happens at the boundary, and how do you manage that? And in a static licensing sense, there's no good answer. If you're in a crowded apartment building, you're going to need a low power so you don't interfere with your neighbors. If you're in a corporate campus or a rural area, you could do with a much higher power and cover more area without causing interference. So it's not one size fits all. But let's think about this from an active spectrum management system. When you first contact the SAS for permission, the SAS can look at a couple things. It can look at your location. Are you in an urban area or a rural area? It can also look at, have other devices been allocated in this area? Even if you're a crowded urban area, but nobody else within 2 square miles has, registered a device, we can start you out at a higher power. Now we can use the sensing data to refine that over time. So let's say we allocate a power in an apartment building, and it's too high because it's bleeding into your neighbor who has a device also. Well, he's going to report sensing data and see your power. So now the SAS can communicate back to you and say, hey, we got to ratchet your power back, you're causing interference. So you can dynamically manage this. And similarly with the indoor-outdoor, as the outdoor devices come along and do their scanning just like cell phones do, if you're seeing outdoor power from an indoor device, now we know to tune that down. So it's a dynamic system, and we don't have to have a static one-size-fits-all, what's the right power. Another example is, it has to do with exclusion zones and how we can better manage the exclusion zone issue. One of the big concerns and why we ended up, initially with a 200-mile exclusion zone is the interference concern from DoD. But in large part, the concerns are not so much what I would call technical interference, but more political interference. Not that the sharing devices are going to interfere with the radars, but what happens if the radars interfere with them and they start complaining and call their congressman? Now you have a political problem on your hands. Well, as Preston mentioned, with receiver standards, we could combine that to effectively solve this problem. Your default allocation might be a 200-mile exclusion zone. Now your device is certified at a better receiver tolerance or better interference tolerance. Well, you get allocated an exclusion zone that's smaller. And this doesn't have to be a formal certification process. It could be self-certification, because what you really want to have is a device manufacturer acknowledging that, yeah, my device can operate under these conditions. And this allows better devices to get better access. And it will bring more efficient devices into the marketplace for more spectrum utilization because they get a benefit by being better. They can operate in more places at more times. So, in summary, I think that we need to really think about this as an active management system, combining sensing data, making it a requirement for all devices out there to do some kind of periodic sensing and provide that information back to the SAS so we can start populating a space-time frequency map of spectrum and start learning about interference. Thank you.
Thank you, Banu. Durga Maladi is Vice President of Engineering for Qualcomm Technologies. He's the Research Project Engineer for LTE Advanced. He's responsible for design, standardization, prototype implementation, pre-commercial operator trials, and interoperability tests with vendors. Durga, Qualcomm has developed an authorized shared access model and examined technical characteristics of small cell operations in 3.5 gigahertz. Can you explain this analysis and the technical characteristics of small cell operations in 3.5 gigahertz that you think will have, along with SAS, an impact on the viability of small cell technologies in the band?
Sure. Let's go to the slides and then we can get started with that. Okay. So first I want to talk a little bit about what we call as authorized shared access. It's also known as licensed shared access in Europe, and there's a lot of standardization activity that we've kickstarted along with our partners. So, to paraphrase something that was stated earlier today, there are two models which are currently used. The mainstream approach of auctions with clearing of spectrum, and then on the right side and on the left-hand side. And on the right-hand side, we have the unlicensed spectrum dedicated to Wi-Fi. Technically, it's not unlicensed, doesn't mean it's licensed to Wi-Fi, but predominantly it's with Wi-Fi usage. What we have been trying to look at is a third model wherein if things cannot be auctioned or cleared off in a given span of time, then we don't want to just throw up our hands and say we are done. Instead, we want to do something about it, but bring something that's very important from the licensed part, and that is the predictable quality of service, which is extremely critical as we come up with these new bands. To preserve that sort of a predictable quality of service, what we wanted to have and what we designed along with our partners over there is to have an exclusive shared use. What it means is at a given point in time, in a given channel, in a given location, one or the other, either the incumbent or the licensee of that spectrum gets to use the spectrum. Both of them do not use the spectrum at the same time, in the same location, in the same channel. That, for once, what it does is it preserves all the qualities which are there in a traditional licensed spectrum. If I'm a licensee of a spectrum, I get access to it and we can actually have a very good predictable quality of service. The second important part is that as we come up with this sort of a technology, then how does one licensee get to know what's going on in the incumbent, and how does the incumbent convey this information back to the licensee? That's where the databases really come in. And from our perspective in Qualcomm, we still see spectrum sharing as something that it needs to be very simple. It is an academic concept that is just about coming into the industry, so we want to keep it as simple as possible. And what that means is no additional requirements on devices. It's got to be as simple as possible, use the existing technology the way it is. If you take LTE, for example, LTE Advanced, we have the notion of carrier aggregation. You can always aggregate two carriers. There's a primary component carrier, which is your anchor carrier. That's something that you always have. It's your plan A, or rather your plan B. But then we have a secondary component carrier that comes and goes. As an end user, I probably don't know and don't care whether this secondary component carrier is either shared with some other incumbent, or it just so happens that I'm near the coverage hotspot of that or not. That's the kind of a view that we have towards authorized shared access. So it's simple on the devices, as in no new requirements. As far as this device is concerned, it's just a new band, and we have 42 bands already. A 43rd band is not a big problem. We'll have a new band, but no additional requirements on the device itself. Even on the network side, we believe that from the radio access network perspective, we don't have to change the underlying technology. What we want is the ability to convey information back and forth between the incumbent and the licensee of the spectrum. Therefore, it's outside the radio access network and technically only between the operator or whoever is the licensee of the spectrum, the ONM for that chunk of spectrum, and the incumbent on the other side. To do this in the right way, there's a lot of standardization work that's going on. There's a very detailed figure over there, which even I can't see, so it's kind of hard to really talk too much more. But you have to bear in mind that this is nothing but an arbiter, something that's in the middle that simply conveys information back and forth. That's our view. Speaking a little bit more about the usage of small cells, what we looked at when we first saw 3.5 gigahertz in the exclusion zones, we said, well, this seems quite excessive. The East, the West, and the Gulf Coast cannot really use the spectrum. So we looked into the assumptions and everything that was done in the analysis, and we said, what if we start using small cells instead of macro cells? Instead of 40 watt transmitters, what if we use 10 milliwatts or 20 milliwatt transmitters? That's a 33 dB difference over there, a factor of 2,000. In other words, if we take the same cellular coverage area today and start using only a small number of small cells, somewhere between 50 to 100 small cells, but they're all operating at 20 milliwatts or so, we were able to reduce from our analysis, able to reduce the exclusion zones quite significantly. This is interference from the whoever is using the spectrum into the incumbent, the naval radars. We looked at naval radars and airborne and other radar activities. So with that, we came to the conclusion that small cells naturally bring in some things which are nice for 3.5 gigahertz. They naturally minimize the amount of interference into the spectrum. What you see over there on the slide is actually a roadmap that we have set up on ourselves. It's a mission statement for us in Qualcomm to go from here, where we are today, let's call that capacity as X, to 1,000 times increase in capacity in the next 10 years. It is something that's important for us. This is what we do. We take a look at everything that we do and say, what is it that we can do to do that? And there are two parts to that story. The first is we certainly need lots of spectrum. That's where 3.5 gigahertz and ASA comes into play. The other part is network densification, a lot more small cells. We'll show a demonstration later on at 2:30 on how a live over-the-air demonstration from San Diego that shows exactly how we can increase the capacity. But what you see over there is as we keep increasing the number of small cells, there's a linear increase in the capacity over there. So we believe that with an extreme densification, a lot more small cells, and more spectrum, we should be able to achieve our goals.
Thank you, Durga. Final question is for John Mylar. As he's responsible for iConnect TV spectrum management solution portfolio, including the TV band geolocation database solution. So, John, you have great experience in developing the protocols and processes for a WhiteSpace's database. What have you learned from that experience that is applicable to the SAS?
Okay, I'm supposed to go back to the first. Going last always is a challenge, not to repeat too much, but I would like to just go back to one thing. Just you may all not know, but iConnective actually is the Telcordia Interconnection Solutions business doing under a new name called iConnective. We're a subsidiary of Ericsson. What I'd like to talk about today is looking at the TV whitespace problem and solution set as an example of an SAS. And specifically like to look at the geolocation database that was used as an evolutionary step to get to an SAS. So a little bit about why I think that's important to understand. Try and go back to the original slide. There we go. The first part is that TV whitespace today is actually a nationwide, as of the recent PN, commercial offering that's out there. There is, it's not really a proof of concept anymore, although we could have key learnings from it going forward, but we should look at it as a commercial opportunity that's already demonstrating how to do interference management. So you might want to ask, what does it protect? Well, it protects the incumbents, and you could assume them to be, for example, the licensed operations in the VHF and UHF bands. There are other entities that are protected. The other entities include, for example, offshore telephony, low-power auxiliary devices like microphones. And there also is the ability to return information to the devices, whitespace devices, those radios, on what channels they can operate on. Keeping that in mind, I'd like to talk a little bit more about how that parallels the NPRM for 3.5. So if you look at that, the first concept is the discussion around tiered access. And I know there was mentions earlier this morning and today that there may not be a tiered access solution in the TV whitespace, but if you sort of envision a little bit, if you look at the incumbent being the TV broadcasters, the federal users, if you then look at the next group of users, which for example are the unlicensed microphone users, they're able to request protection through the FCC and then be granted protection. They actually are prioritized over the whitespace devices themselves. So there is sort of the analogy that you do have a tiered access already in the TV whitespace implementation. The fact that federal databases are being used to understand the incumbents, there are many databases that are brought in from the federal government to use to protect these incumbents. The other idea is that there is protection both geographically based and time based. So you can actually have a device at a particular location being protected. It doesn't move for some period of time. However, other devices come and go as the events are scheduled. So you can already see that in small areas you can protect something for a reasonable period of time, and then when it's no longer operating, let something else participate there. The other point is that there is security. There's authentication of the databases amongst themselves. There's authentication of devices in the databases. And there's also additional validations that are done. If a device is deemed to not be operating properly, the databases are required to no longer allow that device to operate for a period of time. The other comment that was asked or question was about what interfaces are available. As mentioned earlier, go to the next slide, talk about pause. There is a work effort going on in the industry. It's multi-vendor cooperation to devise an interface that's supporting whitespace spectrum access. It doesn't have to be TV bands. It could be any of the other bands. The most important part here is that this particular mechanism allows for different adds to it in terms of either specializing it for a particular vendor or for a particular regulator. It allows for the database to tell the channel what channels to operate or frequencies to operate on, what amount of time they can operate on those channels or those frequencies. But it also allows for a feedback loop from those devices, which could be then used sort of in a closed model to allow for new information to be learned and gained and moved forward. So you can also see in a vision that that may also be useful for the NPRM in 3.5. The last slide is a summary, and some of these were mentioned earlier, but I think they're worth repeating. One is the regulatory policy is actually built in. It's encapsulated within the database. This is important because it's not exposed directly to the devices. The devices can operate without really knowing what's going on in the different regulatory regimes that are operating. The database implementation is quite flexible. As mentioned earlier, rules were actually changed after some of the databases were certified, and very quickly those databases were modified to support the new rules. It's scalable. The idea of databases scaling and using cloud allows it to be supported across a very large region with a large number of devices. Multi-vendor. One of the requests was to see the innovation that could be gained by having multiple vendors. In the TV whitespace arena, there are 2 that are certified, 8 that are conditionally certified, and are moving along that path. And there's also cooperation that was demonstrated in the TV whitespace solution problem set that was developed. That is, the databases actually came together to work to solve several problems. And Peter, on the other end of the table, had mentioned them. One is the calculations, and the other is how the databases quickly exchange information about registrations that occurred. Then the last point here is the future of spectrum access is here today. What's implied there is in the NPM for 3.5 gigahertz, it doesn't have to be futuristic. If you look and leverage some of the technologies we're already demonstrating today, there is enough information there to look how to move this forward. Obviously, there may need to be additional studies and tweaks, but at least you'll see there's an example of using an SAS solving a particular problem of sharing spectrum in the TV whitespace bands.
Thank you, John, and thank you to all the panelists for your introductory remarks. As a way of follow-on questions, one thing that I heard Preston mention was that we should be considering that not just the 3.5 gigahertz band, but that we're creating legacy for the next generation, if you will, spectrum managers and spectrum regulators. So what are the things that we as regulators should be concentrating on to make sure that that legacy comes to be? I'd be interested in everybody's take on what is it that's really going to make a difference in making sure that this is not a one-of type solution, but that this is an ongoing success story for the Commission and for NTIA.
I'll follow up with one, in that we separate policy from band specifics. I think that's the hard part. I think very often people hold the Red Book up as a good example from NTIA, but I think the Red Book doesn't, gives you, this is a policy in the band, this is the details. I think what we want to do, the details will change. The policies are, I think you'll be right, you get the policies perfect the first time, but the engineering details are going to change. So keeping those two separate will let us clearly understand new bands come in and they add technical details, but they hopefully can leave the policy piece alone. And if they leave the policy piece alone, you can approve them much more rapidly.
I have a take on the fact. This is happening as we speak. In fact, 3.5 gigahertz is not the only band in which this sort of spectrum sharing is being considered. In fact, earlier today, Nokia Siemens Networks actually made a reference to a joint demonstration between Qualcomm and NSN in Barcelona 2 weeks back. That was a culmination of the effort that we've been doing in Europe for 2.3 gigahertz. There's a lot of activity there in the same concept, ASA, authorized shared access. The problem statement is very similar. There are incumbents, happens to be the French and the Swiss military. Not all member states in EU have incumbents. There are some member states that do not. For example, Sweden is one such example. The idea there is to unlock that spectrum for mobile broadband usage. And in HC, that's why the initial standardization activity for spectrum sharing in the context of LSA or license shared access happened over there. So it's not the only band. And I would venture that 3.5 gigahertz, what we have here, we have incumbents, but then in the rest of the world, there might not be incumbents in other regions. So when you have device supports of those bands, and then you can easily then leverage that device support, and then you have a broader ecosystem wherein in some parts you have to rely upon ASA, in other parts you do not rely upon it, and therefore as a device itself you don't really need to know whether any sharing is going on or not. So it's not the only band at this point in time.
You can take Vanu's concentric circles and sort of invert the problem, if you like, in the sense that, as sort of what Preston was saying, we can start with policies today that are somewhat conservative, knowing that as those technologies improve, that the engineering will take care of making better and better use. And, it ends up being something like a container packing algorithm. Initially we're going to do a fairly, ineffective job at it. But if you've ever bought anything recently and then tried to return it to the store, it's almost impossible to get it back in the box. But that's really what we're trying to get to. And that takes, a lot of time and effort to get to that level of capability. But that doesn't mean to say that you can't start with something that's a little more simplistic or old-fashioned and then evolve to that. So what Preston's saying is give us a policy that allows that evolution, and then, various industrial technological solutions will come to bear.
I have a question from the audience this time, actually. I'll read it out here. Is it possible to graph the active SAS concepts described by Vanu and Preston onto a standards-based LTE networks? And the second part of that is, would standards changes be needed, and if so, how extensive would they be?
I can take a stab at it. I'll answer the second part first, and that is, do we need standards changes, especially in the technology itself, to enable any sort of spectrum sharing? We believe the answer to that is no. We actually would like to keep it as simple as possible, keep the technology part out of it. In the licensed world, we live in a world where spectrum is extremely scarce, and therefore we pull out everything that we have to make sure that we have maximum usage every last bit of bits per second per hertz out of that spectrum. And therefore, we have interference management in the network, there's interference cancellation, there's add-on carriers, seamless handover when you go from one carrier to the other, measurement reports going back to the network. There is plenty in the technology in LTE itself that we should be able to use. From that perspective, the addition of another carrier, which just happens to be shared, but that's something that's transparent to the user doesn't know, doesn't care. The network knows about it, but the network is the one that controls these devices, and therefore it's okay. That's on the second part of the question. The first part is, I think when it comes down to SAS, the way it's been described over here versus what we are talking about in ASA and what came up in TV WhiteSpace, is the common element among all of them is the usage of a database. There are differences, and there are some subtle differences in the way the database is used, but things are evolving over time, so that remains to be seen. I don't know all the details of everything that's going on over there. But at the end of it, it's a database.
So I think one thing that's instructive here is I think that's absolutely true. There's no reason to have change. But to take the Qualcomm chart here, which is even more unreadable when I hold it up, but what does it tell us? It tells us that we go from about a 50% offload to these small things to 96% of the bandwidth coming from small cells. 4%. So small cells will be 25 times the bandwidth of macro cells. It's hard to believe that a standard that was built around macro cells is the right one. So I think the answer should be no, we don't need to, but we're opening up an entirely new technology opportunity, which I think is part of the argument of the PCAST report, where we're going to now have 25 times more equipment and more access by these new devices, and that's an incredible opportunity for innovation, and hopefully something that is more than just LTE. Perhaps the interference tolerance that we associate with Wi-Fi with the QoS. So I think we should have two answers to that. Yes, it is, but it also really opens up a completely different dynamic for innovators in America to go and pursue.
So the only thing I'd like to add, because the point came up on the usage of the small cells, Release 10 of LTE, which is known as LTE Advanced, specifically was designed for the operation of small cells using LTE. That's why there's something called as EICIC, Enhanced Intercell Interference Coordination, along with interference cancellation that's done in the devices. From that perspective, LTE, I still remember the day that it first came in the US, December 5th of 2010. I was the second guy in the store who bought that phone after working on it for 6 years. And things have evolved a lot. In fact, what is already there in Release 10 and Release 11 of LTE, what we call as LTE Advanced, is significantly more than what is there in the very first version of LTE, which is what is commercially deployed today.
So one of the things I heard Vanu mention a bit ago is describing the scanning that's done currently by cellular systems, by Wi-Fi systems to know what the environment is, which brings up questions like with multi-tier implementation in the SAS that was envisioned in the NPRM, would we expect that each of those different tiers may be participating in some type of scanning operation like that? And if so, what is realizable in terms of the latency of getting data in terms of that sensed environment and how to react to it?
Yes, I think it's a fair assumption that most systems, you heard LTE does measurement reports too, right? And sends them back, and that gives you identities and power levels. Wi-Fi does it regularly. Most systems do that today. Since they do it, there's no additional cost burden to say, hey, you got to scan and send it back. And in terms of latency, how often do they happen in LTE?
It's configurable.
Yeah, what's the shortest?
Typical should be something from 320 milliseconds, 80 to 320 milliseconds.
So you're talking multiple times a second getting these reports. So latency in that regard is not an issue at all with the way systems work today, because you have to do it to support high-speed mobility. What my argument is, hey, we're doing this. Let's make sure we get it back and aggregate it and use it. We don't have to add any new sensing technology on day one. I think evolution-wise, yes, we certainly will. And then you can also supplement it with things like dedicated spectrum sensing nodes that you might put a few around the city to get some additional information going forward. But it exists today. Let's just make sure we use it, configure the phone to send it back to the SAS, and then it's up to the SAS designers to figure out how to intelligently use that information.
Yeah. I have another question here that we've talked about a lot of information flowing back and forth and whatnot. But so my question is, what type of security is necessary to ensure that non-public information can be utilized but not compromised? And the three levels of that is, how can this be implemented at the user and device level? What are the possible enforcement mechanisms, and what are the key operational characteristics of an effective SAS? That is, what does it actually need?
The information you're talking about, is that the information that's in the database?
The information, for example, if you're communicating with a federal system and you're getting information flow back and forth, what mechanisms are there to ensure that somebody holding their device, whatever it may be, is not going to get inside and get that information that's coming back and forth, that's telling them where to go, when to operate, what power levels and stuff. That is, some set of information that gets sent to the SAS. The SAS uses that, and it may send information back out to a mobile device that has to, do some behavior. And what security levels or what's protocol to ensure that doesn't.
I think there's two different security problems. There's security of the data that backs up the SAS that comes from NTIA and other places, and then there's security on the devices. The good news is the devices have a teeny tiny subset of the data, right? They have the information on what they're allowed to do at this place at this time right now and what power level. So even if that's compromised, you're at most compromising very, very local information. The real challenge is on the database side, and I think you do have to have a separation of systems that communicate, where one which contains potentially sensitive DoD information and one that contains more public information, and there's a secure query link in between them. I don't think they can all be in the same system because they don't all have the same security levels requirements.
So to follow up on that, I think in addition to the security of the information that's actually percolating back and forth, it's important to also make sure that, as I mentioned earlier, from our perspective, the devices are out of the picture. The devices don't know that there is any spectrum sharing going on, so in that sense, they don't really need to know from that perspective. The network actually has all that information. Secondly, whoever is the licensee of that spectrum, the incumbent tells the licensee through that database / ASA or SAS controller that this is the maximum amount of interference that can be tolerated. And you could actually make an argument beyond that. There is not a whole lot that even the incumbent needs to know. It's also up to the licensee to make that sort of a judgment call, because it might be that the traffic density is more in one area, not in the other area, within the same geographical domain defined by a certain lat-long coordinates. From that perspective, it's up to that licensee to state that I might want to light up only these cells, these category of cells, or maybe I want to light up a lot of cells at a much lower transmit power. And that amount of freedom really extracts the maximum benefit out of that spectrum, instead of having something that's controlled by the incumbent itself. From that perspective, also when you keep the devices out of the picture, there is a strict command and control structure that is there. The incumbent tells the network basically controls the whole thing. No device just roams around unless the network tells it to. That keeps it simple.
In the PCAST report, it hypothesized a intrinsically government function to decide what was the permissible interference levels at perimeters or boundaries. They didn't necessarily have to be receivers. They could be a perimeter of a base, so you're not necessarily disclosing operation. And so by partitioning the unique government role from deciding who would violate those principles but not determine their validity, you've hid most all the details of government involvement. So I don't have to say I'm testing at Edwards this airplane. This is the maximum energy that can come onto Edwards Air Force Base. And the WhiteSpace system can discipline that without necessarily having to know any of the details about what goes on. And clearly there are going to be some exceptions, but they're the exceptions and they're not the rule.
Well, I need to know one thing, and because it's a two-way street I'm sharing. So I need to know that I'm not allowed to allow interference into that area, but I need to know what that area is injecting into the white space, because it may or may not let certain types of solutions operate. So I do need a little bit more than just don't be here. I need to know that it's really white as opposed to what we tend to call gray space.
And so actually in the peak, to identify particularly the high EIRP radars, there was sort of an assumption that sometimes the system may not be able to tell you about self-protection. And so in some cases I'll know enough to say you're safe to operate. In other cases I may say you'd better put a big attenuator on before you open up your LNA with full gain. And we recognize that there's a whole case there where the system could not provide protection to the device. It would only provide protection to the incumbent user.
Yeah, I think that's the right. You got to think simple. So I think permission to operate is not a guarantee that you're able to operate, and that should be the presumption that the devices have going in.
Right, but if you're going to create that great packing algorithm, you need to work both sides, right?
I think that's a future evolution of the system.
Agreed.
You know, I think everybody has to get comfortable with the information sharing, the security, and then we can go there. But let me also say that if your device is sensing, you will sense the energy that's outside of Edwards Air Force Base, and you can then derive that information and give and no, you won't have anything about what they're doing, but you'll be able to say, hey, if your device can't withstand this much interference, you're probably not going to be able to operate. That's perfectly legitimate.
Thank you, Preston, for bringing up the PCAST report again. A question that I have is, as I look at the PCAST report, it describes an SAS that really seems to be one single system. But when you look at what we've done with TV WhiteSpace's database administrators, we had started with 9, I think we're up to 10, and we're working through getting those stood up. What's the right number, or is there a right number?
I think PCAST actually intended, I mean, that's an editorial comment I have to go back and look at, but I think it was intended to argue that we, in fact, want to give flexibility for massive competition and innovation in the TV WhiteSpace, or in the WhiteSpaces system. We have 9 now. I don't know what the right number is.
Right. I guess part of my question was, is there a number that's too many as well?
Probably these guys might answer that more, but clearly PCAST was trying to be very friendly to massive innovation and value added rather than just yes, no.
Mm-hmm. Let the market decide the right number.
Yeah. I guess there's 2 points to that. There's the technology. Is there an issue with having too many? And can you distribute information? And I think we know there's ways of solving that. The other one, is it viable to have multiple databases or many databases? I do think that's a commercial issue that will solve itself out based on what value adds are brought and what is the service that's being provided.
So how about any thoughts on what types of capabilities that those providers need to have in terms of what an SAS has to consist of to be considered an SAS? I mean, what's the minimal capabilities?
So I think that's really the challenge in this NPRM, is to establish what's the minimum policy requirements to give the maximum flexibility for the vendors to differentiate themselves, but to state very clearly the minimum policy and do it in a manner that's independent of specific issues of 3.5. So do we expect to have receiver characteristics? Do we protect receivers or do we protect transmitters? Those kind of fundamental policy issues really drive it, rather than a lot of the anecdotes about all of what the messages look like and the internal contents. So I think it's important to abstract what's an SAS from how do we share 3.5 gigahertz.
Yeah, I'll go even simpler. I think the minimum requirement of the SAS is to make sure the incumbent's protected. You do that, you're a properly functioning SAS. Even if that means you don't authorize anyone to work, you're still a properly functioning SAS. And that's the minimum. Everything else is differentiation in my mind.
I think that's the part that also came up in some of the standardization activities that we were doing in HC. Minimal protection has to be provided to the incumbents. They are the primary owners. Therefore, they are the ones that need to be protected first. Anything that comes along after that, any licensee of that spectrum from the incumbent happens to use it as an add-on carrier, and therefore it's different.
I guess a question I have for SAS in let's say in any one geographical area, is there one SAS? Are there multiple SASs? And if there are multiple ones, do they share information between themselves? Let's say T-Mobile or Verizon, they set up their own SAS to deal with whatever they're dealing with in an area. So my question is, in any one geographical area like DC, is there one entity? I ask that because in the TV WhiteSpaces, there's going to be a whole bunch of separate authorized TV WhiteSpace databases. Is that same kind of thing apply in this band or not?
I think at PCAST we contemplated that there had to be a relationship among them when you got to the area of exclusive. So I think one of the differentiators between the TV WhiteSpace baseline, and what PCAST proposed was the idea that you could buy exclusive access, very consistent with the Qualcomm approach. And very clearly, 8 people can't be selling the same thing. Right. So there has to be some coordination for exclusive access. The general unrestricted, unlicensed-like access was like the TV Whitespace, one way from the federal government in, but then they had to coordinate on the exclusive access. And that was kind of left TBD for the exercise for the reader.
I think there's 2 ways you can look at that. One is with TV Whitespace, everybody has a nationwide franchise, so they all cover everywhere, and that's when you have to share. But nothing stops your other part of the question, which is if T-Mobile, who owns a lot of spectrum, were to decide to build an SAS for their own spectrum, that's perfectly possible. Yes. Or if they were to build an SAS and, say, share it more like the Qualcomm model with, I don't know, Sprint, that's also possible. So there's no reason why the SAS has to be a nationwide or that there have to be multiples. Once you've got the construct, you can apply it in different ways depending on how you, or let's say who is the licensee or the incumbent and how they want to share it.
So, since we're getting very short on time, did want to get one more audience question. Also, wanted to make one quick message to attendees to please feel free to submit questions at any time. But one more question from the audience is how do you see the SAS accommodating existing satellite Earth stations, including adjacent channel satellite uses?
I think we're learning a lot from the 1755. So I think we will have a body of understanding of Earth stations when the T-Mobile, STA, and all has worked out. And I suspect we'll have a good model to build off of that wasn't available and isn't even available right now, but will be emerging well before this NPRM becomes finalized.
Yeah, I think the challenge is the model. Implementing it in the SAA is not hard, as long as you have the right model.
Right.
Out of time?
Out of time? One more question?
Yeah,
okay.
Go ahead.
So trying to get as many audience questions as we can. How do you see that mobile GAA-type devices accessing the database?
How do you see them accessing the database? I mean,
right now with the TV Whitespaces, I think the question is trying to get to we have different modes of personal portable type devices and how do those
You've got to define what a device is because any device that serves spectrum, so an access point or a base station, has to communicate with the database. But any consumer, so just the edge device, doesn't talk to the database in TV Whitespace. Okay, so a real mobile device generally will not be accessing the SAS because it's going to be latching on to an access point or a base station. Now, if that base station is on a train, then obviously you've changed things a little bit. But the better way to think of it is something that serves bandwidth or spectrum, it talks to the SAS. But a pure consumer should never have to talk to an SAS.
But you do have GAA devices that serve, like the equivalent of a Wi-Fi access point at 3.6 in your home is a GAA device that serves spectrum, and it has to contact the SAS in the same manner that the other devices do. I want to make one point that, today we kind of have, as we had in the Qualcomm charts, 2 models, the licensed spectrum and the unlicensed. We're looking at something different. What we have in the NPRM is you can't have pure licensed, unlicensed, or pure licensed in the presence of an incumbent. But Tier 2 is a pretty good approximation of the licensed model. Tier 3 is a pretty good approximation of the unlicensed model. The main difference, and this is important and it goes to the SAS intercommunication, the main difference between unlicensed today and GA, in my opinion, is that you do have to have admission control to the network. Because if you threw enough GA devices in there, the aggregate interference would end up harming the incumbent. Whereas in unlicensed today, you throw enough in there, well, they harm each other, and we've been pretty good at working that out. But that doesn't work when you have the incumbent. So they do have to contact the database, and there's the possibility that the SAS might say, "Oh man, we got too many of you. You can't go. We're at our interference limit." So, and that has to be coordinated between the SSs as well, because we can't have them all independently authorizing GAS devices to a specific.
I would argue that's just a special case of exclusive. It's just not
Yes.
1,000 are exclusive rather than one.
Yeah, it's an aggregate limit as opposed
I would
to.
just add one other thing to that. In the context of, and that's specifically in the context of LTE, this is how we see this would work. As a device, you don't know about the existence of the other carrier. You're on a primary component carrier. This is some traditional licensed spectrum. And then you're advertised the presence of another carrier. That's when the device actually goes and performs and that's the only time that it does measurements. It doesn't do measurements on its own, and it doesn't go off transmitting in the traditional spectrum either. Goes, performs measurements, goes back to the network and says, this is what I have, what do you want me to do? If you get handed over, that's great. Otherwise, you just stick to the primary carrier. And that sort of an authorization, therefore, is always through the network, not directly with the device, and there's no special requirement on the device itself.
I think we've spent our time here, and we certainly thank all the panelists for their participation.
Yeah, thank you very much.
Okay, so we're going to take just 30 seconds and set up for we're starting the technology part. We're going to have a technology overview presentation, and then we're going to have some technology demos back in the back of the room. So please stick around. We'll be ready in 30 seconds.
Yeah, short talk and then just no actual physical demo.
See you too.
Hey, good to how are you? Good to see you, sir.
Like I said, this is really exciting. I keep thinking one day this will be well, hopefully better than that. Right.
I suspect it's better to keep this around here. Hopefully if it stays, otherwise I'll have the Marco movement.
Julie's actually going to introduce you.
Oh, super. Thank you.
All right, thank you very much.
Oh, no problem.
Yes. Nobody's talking about ACS now does force supply. Yeah. Which you can't do today very quickly. I know that. It's so much better world.
Yep. Okay.
I can either introduce you or maybe you just say a few words on your background.
Yeah, that would be good. She suggested you were going to talk. I think you can introduce me.
Just a couple seconds to introduce
you. Sure, no problem.
But your slides, in order to have the slides projected and picked up, they're going to run off of that computer.
Okay.
So that should do the remote.
And the clicker is just the next.
Yeah, forward and back.
Okay.
And then if you have an issue, Ramon sitting there, you can just say next slide, please.
And I can see the slides on the screen.
Yes.
Okay.
Yes. Your eyesight's better than me. So let me pick it up. Yeah. We've got a couple more segments left today. We're going to have a presentation by Dr. Milind Bhakat. He is currently a distinguished member of the technical staff at Alcatel-Lucent Bell Laboratories, where he conducts research on next-generation wireless networks. I won't go through all the details, but he's got an extensive background in the technology, and particularly with dynamic spectrum access. He's going to provide a short small cell technology overview, and then that will be followed by, we've got the exhibits up in the back corner. Please be sure to stop by and see the technology, especially for the folks that went to the trouble of bringing all that equipment over here. So thank you.
Thank you. Thank you, Julie. So in the next 15 minutes, I'm going to... okay, can you guys hear me? Better? So, and I want to take a quick look at where my slides are. There you go. So in the next 15 minutes, I'm going to try to provide you an overview of the small cell technology, and specifically from the point of view of Alcatel-Lucent, and try to connect that to the 3.5 gigahertz small cell band that's under discussion over here. I would like to gratefully acknowledge one of my colleagues, Rob Sony from Small Cell Technology team, in preparing this message over here. So as a wireless phone explosion and high bandwidth applications continue to grow rapidly in coming years, estimations have shown that the per user traffic will continue to increase over the next 5 years, typically at a rate of 4 times per user per month, and aggregate traffic growth of about 25 times from what it is today. So if you are an operator, the goal that you have is to essentially increase the capacity to sustain a certain quality of service experience and also reduce the cost at the same time. And there are many ways of increasing capacity, and some of them are illustrated over here in the chart that is popping in front of you. As you go from left to right, these techniques will give you a different type of capacity improvements. So techniques like cell splitting or adding additional carriers often tends to be a very slow process, and it's often expensive. On the other hand, techniques like carrier aggregation, MIMO, EICIC, or coordinated multipoint, or even active antenna arrays, they give you anywhere from 10% to a factor of 2 improvement. The most promising techniques are the last two techniques. One is the small cells and the so-called centralized baseband implementations. In fact, the small cells are expected to give you a linear growth and capacity improvement, as was pointed out by Qualcomm team member today in the panel. And small cells is the topic of our conversation today. And we believe that in years ahead, we have to combine all these techniques to achieve the 25 times traffic the capacity growth that we are looking for. And the Alcatel-Lucent Light Radio platform that was announced about 2 years ago is essentially solving this problem. And this chart will actually illustrate that the light radio network that we are envisioning, the small cells will give you up to 6 to 10% capacity improvement, and they will continue to be a critical part of creating wireless capacity for the future. So let's take a kind of a basic look at what the small cells are. And I think small cells is a broad term that encompasses cells that are deployed indoor as well as outdoor. The indoor cells are typically called femtocells or picocells, and they could be deployed inside homes, or it could be deployed in places like enterprise buildings or even public venues. There are so-called outdoor cells, which are often called in industry parlance metro cells, and in addition to those, you could have the notions of Wi-Fi hotspots, which are in typically unlicensed band, and also a notion of what are called as remote radio hertz, which are part of distributed antenna systems. And small cells are going to essentially help you give better coverage, better capacity, and a better customer experience, and deal with the new devices, as in the smartphone explosions that you're seeing, and the new type of services that need location context or need additional contextual information from your surroundings in a much better way. And also these cells often may have a different way of organizing subscriber pools. So they could be private, as in the cells that are in the homes often would be private cells, which only the home members would be using. Or they could be public cells, where anybody who enters at a given small cell coverage area can actually access the capacity provided by that cell. So Alcatel-Lucent has been at the forefront of trying to create small cell solutions, and we have a comprehensive award-winning portfolio that targets multiple technologies and multiple deployment scenarios, and it's illustrated in the charts that's coming up. It ranges from low power small cells right up to very high power, up to 5 watts per channel small cells. And in this particular slide shows only a subset of the portfolio. There are some low-power versions for which the brochures are sitting over here on the table. So I'll come to that actually. So the first set is the so-called 250 milliwatt 3G cells. These have been widely deployed in the customer networks already, and they support multiple bands as in 850, 1900, and 2100 megahertz. The newly introduced LTE small cell supports 2 channels at 250 milliwatts, and again, this is for indoor deployment. The most interesting is the outdoor metro cell. Even though there are multiple configurations shown over here, essentially it's one product family that can be configured to support multiple standards and multiple deployment scenarios. And it can go from 1 watt up to 5 watt. The last piece, number 7, is a purpose-built small cell where the antennas are external. So one of the customers is looking for an external antenna rather than an integrated antenna. And all these units are distinguished by the fact that the baseband unit is integrated into the small cell. So the radio, the antenna, and the baseband is all in a single enclosure. The last but equally interesting is what we call as the metro radio outdoor, and it's shown over here. It consists of 2 pieces. Is the the radio part, and the baseband unit that's at the bottom. So think of this as a remote radio head that is mounted on a pole top. There's a fiber coming out of the base of this, and it runs CPRI, and that fiber can take essentially your digital INQ to a remote baseband processing unit, and that distance could be up to 15 kilometers. So it allows you to essentially have a distributed antenna structure, if you want to call it, or a distributed remote radio head implementation. Going to how could you leverage this small cell portfolio to deploy various scenarios, and those are illustrated over here. So you can take a 250 milliwatt LTE small cell and essentially deploy it in an indoor hotspot like this, or even bigger hotspots. The 1 watt outdoor integrated baseband unit small cell can be used for deploying coverage in public hotspots as in outdoor coverage, or you could create indoor coverage by deploying the cell outdoors. And it could be also used in places where you have a coverage hole. The 5 watt external antenna unit actually could be used for supporting up to 200 users in very large public areas. So if you go to a Woodstock like music setting, you could see a base station like this providing quality data coverage. And it could be also used in rural areas to provide broadband access. And a unit like this, for example, the Metro Radio Outdoor, could be deployed in places like stadiums, where the radio heads are in different parts of the stadium, but the baseband unit is situated somewhere in a small room where all fibers are being brought over, right? So it's probably instructive to take a slightly closer look at our light radio concept, because it's not only innovation in terms of architecture, innovation in terms of radio, but it's also innovation in terms of how the product is architected. It consists of 3 main parts. It contains what is called as a metro dock, and the metro dock actually aggregates the backhaul capacity, the power distribution systems, as well as a small cell router into a single enclosure that can be mounted anywhere, ranging from walls to pole tops. The second piece is what is called as a RF module, and this RF module essentially docks onto the metro dock in a very easy fashion, and it supports multiple standards, as in WCDMA, LTE, and up to 5 watts of radiated power. And it essentially supports multiple bands as well as integrated directional antennas. Another important piece of this is what we call as carrier-grade Wi-Fi that is already part of this solution. And it's another innovative piece which contains a module that can be essentially plugged onto the bottom of this metro cell. It is a dual band, dual concurrent, so it supports 2.4 as well as 5.1 spectrum simultaneously, and it supports 11 and 2x2 MIMO, and up to 256 connected users at any given point. And the same the same radio module could be configured either as a backhaul or it could be configured as an access. And also, when you're using it in the backhaul fashion, you can do daisy chaining. So if you are mounting it on one pole top and you need to connect to another pole top over a wireless backhaul, you could create that kind of daisy chain before you reach a fiber-connected endpoint. And this unit allows us to also have a seamless roaming between Wi-Fi and cellular to improve the user experience. So another important thing is that the so-called multi-dock version of this, where 2 docks are simultaneously integrated in a single enclosure, you could use that enclosure in a very innovative fashion. You can create so-called multi-standard configurations where a WCDMA can coexist with an LTE, or you could create multiple band combinations. And going forward, you can even support things like carrier aggregation very effectively in this single configuration. And the same box can be converted into what we call as a remote radio head, the kind that is shown over here. So a multi-dock structure like this can become an all-encompassing metro cell deployment architectural model. So I'm going to switch gears and talk a little bit about what are the considerations when it comes to deploying metro cells. And there are 2 main ways of deploying metro cells. The first one is called shared carrier deployment. And by shared carrier deployment, we mean a macro cell and the small cell that is deployed in its coverage area. They both use the same spectrum channel. And inherently, that leads to certain interference interactions. And even before we start worrying about these interference interactions, it's probably important to understand that field studies have shown that the traffic within a metro cell, in a macro cell coverage area often tends to be spatially clustered. So if I put a metro cell right in that clustered traffic hotspot, I can have a very good effective traffic offloading. In fact, our experiments have shown, our measurement analysis have shown that 50% of the macro cells in an operator network are amenable to 50%, greater than 50% traffic offload. Roughly about 25% of the macro cells can do anywhere between 25 to 50% offload. But unfortunately, when you're doing shared carrier deployments, you have to be very careful because the effectiveness of offloading depends on three different parameters. First, the distance from the macro cell on which you are in which you are embedded. So greater the distance from the macro cell, the better effective small cell is in terms of doing offloading. The second important characteristic is the amount of traffic in the hotspot. The greater the traffic, the better you're going to be in terms of offloading. And the number of hotspots. This is a bit of a tricky point because if you have too few hotspots, you can do good offloading. But if you have too many, then you have inter-metro interference that you have to deal with. The key takeaway I want you to go away with is that shared carrier approach on an average gives you lower economic return, but it's still effective in terms of providing 30 to 35% traffic offload. It offers effective capacity and coverage in some use cases, especially indoor locations. And for operators that are very spectrum strapped, as in they don't have enough spectrum holdings, this could be the only approach that they can go with. And the interference interactions that we were talking about unfortunately lead to what is known as efficiency zones. Because field results have shown that not all locations are amenable to effective metro cell deployment. The closer that you are to a macro cell, the increased interference that you see, and the smaller is the metro cell coverage area. And also it leads to what is known as high uplink pollution. And it can lead to the receiver blocking that often is due to the limited dynamic range of the receiver. So the deployment guideline is that if you have a macro cell, there are two regions, the so-called exclusion zone and the low efficiency zone, in which the metro cell deployments in shared carrier format are not going to give you effective offloading. But away you go from the macro cell, as in the moderate efficiency and the high efficiency zones, you can get significant offloading performance. The alternate way of deploying metro cells is what is known as dedicated carrier. And the idea here is that the spectrum channel that you're using in a macro cell is completely independent of the spectrum channel that you are using in the metro cell. So for example, if you're an operator with 700 MHz license and an AWS license, you could allocate AWS to metro cells and 700 to macro cells. Or you can take a 700 MHz channel and split it into 5 MHz channel each, and give one to macro and the other to metro. And the dedicated carrier deployments are typically very effective in terms of capacity of creation as well as offloading efficiency. Because there is no interference interaction, there is no size constraint that you have to have on a metro cell coverage. And it could be easily configured through cell selection priorities and thresholds. So the greater the number of metro cells, the greater offloading efficiency that you can see. And that was also reiterated by Durga during his panel presentation, that you can almost see linear capacity increase to some extent. And also, in terms of cell border throughput, we see that the dedicated carrier deployments are quite effective. There are some advanced techniques that are being talked about in the industry to improve the shared carrier as well as dedicated carrier deployments. I'm not going to spend too much time on them. I'm going to flip through them. Let me come to the main part of the discussion over here. How can you leverage 3.5 into small cell deployments, right? Predominantly, we have talked about how 3.5 can be used in what is known as small cell access. And we also continue to believe that it would be very effective in small cells, especially the priority access channel portion of 3.5. It could be used to provide additional capacity in a dedicated carrier system, and it would be very effective in terms of great offloading efficiency. And having a priority access, especially to operators, that would enable even wider deployment of small cells over time. Another application that has been less looked at is what we call as a small cell backhaul. And small cells are typically expected to be deployed on utility poles or in urban furniture, and the installation height is typically 8 to 20 feet. And all these locations where you're going to deploy metro cells is not going to be effective or easy to have a fiber routed to these locations. In fact, the number of wireline locations where you will have metro cells deployed is going to be much smaller than the number of locations that you want to deploy metro cells at. So you need a good wireless backhaul solution. And because you're deploying in the clutter, the line-of-sight backhaul solutions that operate at higher microwave frequencies like 30, 60, or 90 gigahertz, 80 gigahertz are not going to be very effective. So you need a non-line-of-sight or a near line-of-sight backhaul solution. And sub-6 gigahertz spectrum like 3.5 will be very effective in providing such coverage and capacity is what we believe. Last but not the least, I think 3.5 could also be very relevant in what we call as local loop augmentation. So in many parts of the world, copper continues to be a dominant form of providing access. And increasingly, even though there are innovations like vectoring that are improving capacity, there needs a more cost-effective way of increasing capacity. And fixed wireless access, when combined with DSL systems, could give you that way of improving capacity. And 3.5, especially priority access 3.5, could be an ideal way of doing that. And because you are mounted on rooftops, and because multi-antenna systems at 3.5 typically tend to be much smaller in size, you could effectively do very high capacity systems and leverage 3.5 in a good way is also one of our positions. I'm going to, in this last slide, give you a bit of an overview of what we are trying to work in the lab. So this is going to show a research program that has been going on for the last 3 years. It's called White Cells. And the idea here is really very similar to what the 3.5 proceedings is talking about and what PCAS is talking about. And the idea here is that you have a small cell complex, a slew of these distributed in space, which are controlled by what we call as a cognitive spectrum server. And each of these small cells are equipped with a wideband spectrum sensor. And they continue to sniff the spectrum bands and report these measurements into the spectrum server, which creates what we call as a radio activity map, and a radio environment map, and uses that for doing better spectrum management, better scheduling, and so on. And we have an operational prototype that we actually built in the lab using the digital TV WhiteSpaces. And this prototype is actually integrated with Spectrum Bridge pre-certification database. And these base stations, both indoor as well as outdoor versions, are currently operational in our Murray Hill network. So if you happen to come by, we can definitely show you a demo. So I think with that, let me conclude. If you have any questions, please come by later, or even now I can entertain them. Thank you. Thank you.
So I want to thank Milind for that great overview. Please join me in thanking all the panelists today for their insightful comments. I thank Julie Knapp for his remarks and Chairman Janikowski as well. Please give him a round of applause. Thanks also to all of you for attending, all of our viewers online for watching, and for the FCC staff involved in planning today's event. One final note, as mentioned earlier today, we have pushed back the reply comment deadline for the NPRM to April the 5th. We're hopeful that today's conversation will stimulate some additional debate on the record on the important issues raised in the NPRM. To conclude today's program, Qualcomm, iConnective, and Spectrum Bridge have set up exhibitions and demonstrations in the back corner here, and Alcatel-Lucent has their small cells up here for folks to come by and take a look at. This will conclude the web stream portion of the event. Thank you all very much for coming.